and we will move now to the session number 3, Networked Artificial Intelligence. The first keynote speaker is Sergio Barbarossa from University Rome La Sapienza.
The real challenge is to organize this grand challenge number 12, because as you can see from the title, it's a really cross-disciplinary activity that, as you will see, it involves many projects already working within Restart. So here is just the list that I have now of all the people that contacted me during the call that we had. And so you can see there are already many projects where somehow there is a merge between artificial intelligence and networking. Now, a quick summary of what I'm going to present. Well, first of all, I will just spend 2 or 3 slides with this bird's eye view on the machinery that artificial intelligence can provide. I will do that also for the scope of stimulating some discussion between us of what we think would be more appropriate to use in our field. Then I will introduce this path going towards AI native networks, and then I will focus on the main aspects where AI and networking interact with each other. I will start with knowledge representation and communication, then AI for networks, and then networks for AI. And finally, I will conclude with some intelligent services or verticals. So just as a very global view, I put this slide here because many cases we tend to interpret AI as machine learning. Clearly, machine learning plays a fundamental role in AI, but cannot be confused with AI. In AI, there are many other things, among which I would like to cite knowledge representation, perceiving, communicating, acting, uncertain knowledge and reasoning, causal relationships, etc. Then within the big machine learning ball, we have the typical, supervised learning, unsupervised, reinforcement learning. Within this area, we have neural networks, and then deep neural networks, and finally generative models. And I will use some of these tools in different contexts. But before starting, let me start with maybe a fundamental question that many of us can ask, which is how can we choose between a model-based approach, which is the one we grew up. We grew up with model-based. We all studied how to model reality, maybe with a mathematical model, etc., and design our systems, etc. And then we had a very, I would say, knowledge-centric approach to the problems you wanted to solve. Now, if we look at the counterpart in deep learning, it's not a knowledge-centric, it's typically data-centric approach. The machine has to learn from the data that we give to the machine during the training phase. The second point is that model-based approaches are typically very tuned, specific to a task that they want to solve. Conversely, in the deep learning case, typically a deep neural network is model agnostic, doesn't know exactly which is the application. It's very general purpose. And finally, the big difference is that in the models we were used to adopt, typically the number of parameters is very limited. On the contrary, with the deep neural networks, especially in that case, the number of parameters, the coefficients in the DNN, the deep neural network, can be huge. There are now machines with hundreds of billions of coefficients in the big neural networks. So if we were to ask, okay, how can we choose? Well, I like to propose this kind of view. Essentially, I call it a spectrum of architectures. What do I mean? I mean that we can go from one case, the deep learning case, where on the left side, where we just have the deep neural network, and on the other side, on the right hand side, we have our loved old model-based approach. But then we can also be in between, What do I mean? I mean that typically, for example, if we start from here, so this is our typical story, how we model a problem. Maybe there is some iteration with which we want to minimize some objective function, whatever. But then it is typically that to drive the solution towards a class of solutions that is good for us, we typically put regularization terms, for example. But then there are parameters that we have to tune, okay? Then many times these parameters are tuned manually, or you need to do cross-validation, etc. Well, then you can start thinking of using a neural network to train these hyperparameters. So underline we have a model-based, a model which is given by the physics, whatever it is, but then the parameters of the model are learned, okay? So it's like we move from the purely model-based to something that has some kind of learning to tune the hyperparameters. And then you can move, for example, here in what is called deep unfolding. In that case, for example, this is useful when you have a constraint on delay, and you can say, okay, I want to solve my problem, then I have some knowledge of the model, then I repeat this model into a fixed number of layers, as in a deep neural network, but the layers are tuned to the model that we know, okay? And then we train this neural network to train all the hyperparameters across all the stages, knowing that everything has to stop within a finite number of layers or steps, if you want. Okay? So why I presented this? Because I would say that our community has a lot to contribute to this field if we think not purely in terms of purely data-centric approach, but in this model-based machine learning, there is a lot that we can do because we grew up with building models of reality. So let's use it. No, don't forget them and just use a deep neural network, because otherwise we have problems of explainability, etc. Okay. Then if we look at the path leading to AI native networks, of course we can start from 5G and adopting some tools from AI, typically machine learning, to improve the efficiency of our networks. And there are already many standards on this that talk about different levels, the RAN, the OAM, 5GS, etc. But then if we look at probably at one of the ways in which 6G will be, typically we tend to say that 6G is going to be AI native. What does it mean? It means that since the very beginning, AI tools, machine learning, whatever, will be a core component of the network, so that when we design the network, we know this in advance. The overall architecture will be the composition of all these functionalities that are built using AI. This architecture is going to be designed to continually learn from data and adapt to new situations, to improve performance, enhance efficiency, to enable a proactive behavior through prediction, which is a fundamental step, improve security, etc. Now, some of the key features of this network is that we can think of the network as if you want, a huge computer or a huge system for sharing knowledge among different entities, be them humans, machines, whatever. And this is one point. So the network is not anymore just a bit pipe, but it's a knowledge sharing system. The second point is that we want to take advantage of digital twins, so digital twin networks, because this gives us a way, when we merge digital twins with AI, we have a great tool in our hands, because in principle, imagine reinforcement learning. Instead of learning step by step, which is the best action now, if I have a very good digital twin, I can predict from now on for a certain time until the accuracy of my prediction will be good. And then I decide in advance which is my best move knowing what is going to happen in the near future, which is much more powerful than plain reinforcement learning as it is used today. Then the other fundamental point is how to disaggregate services and network functionalities into microservices, possibly running in the edge cloud, because in this way we can distribute intelligence and bring them as close as possible to the end user. And this is especially relevant when we have delay-sensitive applications. And finally, one of the other things that is touched upon in several projects is how to create intelligence on-demand services, meaning that we bring intelligence wherever and whenever it is needed, maybe using some robots or UAVs, about which we have examples of applications, real ones. One is on the top of this building from our colleagues from Catania, Giovanni Schembra, whom I don't see, but I'm sure he's going to present something about the fleet of UAV. And maybe if I have time, I will run a video about an intelligent robot that is moving and looks like it is intelligence, even though it doesn't have, of course, any intelligence. Okay, then let's start with the tools. First of all, before going into machine learning, I will just mention knowledge representation and communication. I will just touch some of the topics. Then, of course, I cannot cover in depth, but I do it to stimulate a discussion. Maybe people who are interested can contact me later on. So one point that I want to make from a signal processing perspective is that if we are dealing with network traffic, from a signal processing perspective, it's like having a signal or vectors defined over the edges of a graph. It can be proved, in theoretical terms, that the best way to handle this kind of signals is not a graph. A graph is important, it's fundamental, because the data are defined over a graph, but to do something better in our estimation, prediction, etc., it's better to use, in this case, higher order spaces. For example, a simplicial complex, which this is one case of simplicial complex, where you see we go beyond the pure presence of nodes, edges, but we can have triangles, polygons, etc., which represent higher order relations among the data. So what we did with this, we took real data traffic from this network in Germany. It's an available data set. And then we said, okay, let's derive the fundamental trade-off between accuracy of the representation of this signal and the sparsity of the representation. We would like to represent an overall pattern of traffic data with the minimum number of parameters. Then we found the fundamental trade-off between the number of parameters that we use and the accuracy that we can achieve. The different curves refer to a graph, this one on top, and then a simplicial complex, which is a higher order structure, and a cell complex, which is an even higher order. And then you can see that playing with these tools, we can achieve a better trade-off in terms of sparsity and accuracy. Okay, now you can ask, okay, what do we do? What's the application of this? Well, for example, suppose that we want to run a digital twin. Now, one of the fundamental problems in digital twins is the synchronization between reality, the real network, and the digital twin. To enable this synchronization, clearly, if we minimize the number of parameters that need to be exchanged between real and digital world, this is fundamental. So you see, the same curve that I've shown before can be used exactly on this, because it can be proved that if we want to represent the overall pattern of data traffic along this network, the number of samples, points where we measure the real traffic, this number of measurements is related one-to-one with the sparsity, which means that for the same accuracy, we can reduce the number of samples and the number of data to exchange between real world and digital twin. Okay, then we also, just because we developed within this project these higher order tools, we also defined a new architecture for a neural network, which we call the topological neural network. If you want, for those of you who are used to graph neural networks, this is a kind of generalization because it starts from data defined over a high order space. And we prove that in many cases, some of which quite complex, like classifying proteins, etc., we beat almost all the state-of-the-art competitors. Okay, then second application of knowledge representation is this field called semantic communications or coding for machines, call it as you like. So what's the point here? The point is that if you establish a communication link and there is a clear, and there is an application running on top, which is requiring this exchange of data, supposing that the task is, I don't know, recognizing objects in an image or classifying images, etc., then we can say, okay, we can devise a coding scheme, so a source coding scheme, such that we transmit in a hierarchical way, depending on how much the objects present in the image are important in a semantic sense. So for example, suppose that we are taking a video from a web camera on time. I'm running out of time. Oh, wow. Are you sure? But I didn't start at 2. It's not my fault. I didn't start at 2.
I mean, depends on how much time you give to the other two.
20, 20, 20, no?
Oh, it's 20, 20, 20 or...
No, it was a bit more for me. I started 15 minutes later and then...
So let's...
Okay. So the idea is that we just send what is necessary at the receiver to run a generative AI triggered by the data that we send, so that at the receiver we regenerate something, and then we derived a sort of fundamental rate distortion trade-off, but where now the distortion is a sort of semantic distortion. What was the meaning, for example, here, the presence of pedestrians, cars, traffic lights, etc. And then you can see that for the same distortion, we can achieve a number of bit per pixels that can be even half of the state-of-the-art in source coding, which is a big improvement. Okay, then let's move to AI for networks. So here is an example where we optimize the service placement in the edge cloud and the resource allocation, where by resources we mean bandwidth, so radio resources, CPU clock, so computation resources, and storage. Okay? And then what we do is we say, okay, the fundamental trade-off should take into account these three components, and then we say, okay, suppose we fix accuracy of classification task, and then we find the optimal trade-off between energy spent from the mobile devices and latency, where latency here measures the overall latency. We call it actually service delay, which means which incorporates transmission time, processing, and decision, the time necessary to take the decisions. Okay, then this is a contribution from University of Trento, where they implemented this digital twin network, and they shown how incorporate in some way to predict the behavior of traffic in terms of time, you can better synchronize the digital twin with the real world network. And then this is an application to integrated access and backhaul, where you want to find out how to, allocate frequency sub-channels to all these channels here, using Q-learning, so reinforcement learning, essentially. And this curve just shows that you can do better than conventional approaches. And then we move to the third case, which is the other way to use, to merge AI and networks. So how networks can be useful to facilitate the deployment of a pervasive AI services. And another important contribution here is the following. Suppose that you have data, you want to process this data, and maybe you want to process them using a deep neural network. And then what we proposed here is the following. You take this deep neural network and you split it in two parts. One is running at the transmitter side, the other one is running at the receiver side, and then you design the architecture of this network to have a bottleneck in the middle, so that at the same time that you do inference, you also compress your data, so that you transmit the minimum amount of data necessary for the receiver part of the DNN to take the right decision. And again, we formulated the overall problem in order to strike the best trade-off between decision accuracy, service delay, and energy consumption. And this is an application of this. And then another example is when before I mentioned the inference phase, now I mention the distributed training. So suppose that you have different data sets in the edge cloud. You have different edge servers. They run their own inference task to train their own deep neural network. And then you want to take advantage of the network, for example, using federated learning to improve the inference task. And this is what we do. And this is an example of, for example, the classification accuracy. But you see, we put a target at the beginning. For example, we ask 0.70% of classification accuracy. And then you can see that all the machines will converge through the federated learning and coupled with Lyapunov optimization to the objective that you have in mind. Then, for example, here we switch to a different KPI, 80%, and the overall system will converge to the new level. Okay, then in terms of intelligent services, 1 minute. Okay, this is a demonstrator that is running. This is a joint work between University of Perugia and Roma Tor Vergata, where they built this demonstrator using a mobile robot. The robot takes a video, it recognizes a person. You see the robot recognizing a person, and then moving. And while moving, it will also switch between different radio access points. It is also multi-rat because it goes from Y gig at 60 gigahertz to the 5G. And then I have a video. There's not much time to show it, but in the video you will see this robot that follows the person that recognizes. It goes after this person. Every time it's switching, and you don't see, you really have the feeling that the robot is understanding. Of course, everything is done on the edge server, and the edge server moves along the path because the service has been disaggregated into several microservices, so the computations moves across the edge cloud, and then the latency is very small. This is why you have this feeling that it's the robot that is taking the decision. And this is just an example showing how the resources are used. And then we have several other applications to computer vision from Carla Chiasserini and his group in Torino. And then uplink streaming, AI-aided uplink streaming, and also AI for assisted extended reality. And finally, the application in the project Watch Edge, run by Guido Maier from Polytechnic of Milano, about bringing AI surveillance to rural community. And here there are some interesting applications where they show that you can orchestrate, you can augment, first of all, the data set to have superior classification capabilities to recognize objects, in this case animals. And also the last application that I will mention is this one involving a fleet of UAVs, and I will encourage all of you at the end of the session to go on top of the building to see the real application organized by Giovanni Schembra. I finished. Thanks. Sorry for taking maybe too much time.
So, the next speaker is Gabriele Elia from TIM.
Good afternoon, everyone. Thank you for calling for this presentation. I will try to make some suggestions about what we are doing in Restart and also in the company about AI and networks. First, I would like with a joke. How many have tried this piece of on both ChatGPT or Gemini? If you ask, I say in Italian. In English, it's the same anyway. I tried this morning. It makes the same result in English. I have a small problem. Alice has 3 brothers and 2 sisters, 2. How many sisters has the brother of Alice? Both ChatGPT and Gemini, both the paid version, and they answer this way. 2 things, at least for me, come from this. The first thing is that hallucination, all this stuff, is something that is very simple to see for experts, like a 60-year-old children, but it could be quite difficult to understand from people not in the domain. So we are still a little bit behind what's going on. The second point has been very interesting talking with my colleagues, because it happened as something that I heard from a different professor, Professor Norman, that invented one of the major people working on usability, is very famous, the coffee pot of the masochist. If you remember the picture of a coffee pot that makes coffee on your hand instead of working in the cup. Norman, once in a conference, I heard him saying, when technology becomes so deep that also wrong mistakes of the technology are appreciated by people that are able to overcome it, it's a triggering point. And the example that he was saying a few years ago was that if you want to change the APN, the APN in mobile network on iPhone is very difficult, but people on their phone say, oh, I managed to change it, instead of saying they should change this feature that is hard to change. Because when I talk with colleagues that are working in AI, they say, it's your fault because you made a bad question. You should ask, you are not a good prompt engineer, say what you say. You should say, I'm in the context of a family, I want to say, no, if you, of course, if you create more context about this question, the question works. But when people started to find a problem in people and not in the technology, it's because they are really fond of technology. And it's a really, for me, a triggering point for the fact that it's really something that is pervasive on a level that we don't imagine. In fact, there are provisions that AI will generate billions of revenue in the telecom market. The violet part is for network operation, monitoring, management, especially. No? So it's by far the part that analysts think that will be the part going on in the networks, and in fact it's also something that is happening in TIM, in my company. There are plethora of paper coming, of course, in this moment, also from the business point of view, not only R&D and university paper, companies and consultants that say that AI will be the next Graal of telecommunication, and we can also share, for example. These are all public papers that I simply look at the last weeks. And it's also very funny, because if you ask to CTO, 95%, NVIDIA asked to CTO of telecom operator, 95% you are using AI. And, but if you ask, how long are you using AI, they say less than 6 months. So 36% say it's less than 6 months. And no, more than 6 months. So 74% instead is less than 6 months. So it's just this is a very, very recent analysis. And we started, like many companies, a few time ago. The first lesson, as usual, you can imagine, is the problem that when you move from the modeling or the deep learning modeling to the actual application, the quality of data is one of the key points. No? this is also a suggestion for digital twins. So, but one of the first points that we had to manage is that AI needs data, and data are not so good always in company. It's hard to find data, but it's also hard to find good data that are not biased, are not skewed, or bad data. I think I can move. We get back on the fact of data, but another point that the lesson we have learned is that at the end, data visualization coming from a system also is a very strong point for making human in the loop. No? Is not such a strange conclusion, but it should not be overcome that we need to give to people the tools that allow them to feel comfortable and trust the results. The first example of the children and the sister maybe is something that is teaching us we need something to understand if things are going out well, and if things are usable also for people that are used for 10 years, 15 years to work in the company. And so data visualization is something that should not be given for granted in AI project. Then we worked in a number of topics. One, for example, was assurance. It seems funny, but I remember well the first project that we made was that we have a lot of. We were starting to give football games on IP, and the traffic was increasing during games in a specific way. And this increase in traffic on some links and not on the links of the network, because what happens that if you have Bologna-Roma, traffic grows up in Bologna and in Roma, and not so much in Torino, Milano, and Bari and Catania. And this was triggering the alarm system in the network to something. There is something strange in these places. Why traffic on this link is growing so fast? So we have to put manually, there is a game this evening at the 8, and it's not a problem. Filtering alarms in that way was not a good way of filtering alarms. And instead it worked using some simple machine learning model. Also it was working because when games were closing at the end of the game, the traffic was dropping very fastly. But dropping in traffic again was triggering alarms to people in the network operation, because if on a link that is giving 40 gigabit per second of traffic, you slow down in a few seconds to 2 gigabits. That was what happened, 2 gigabits per second. That was happening at the end of a game. It was by the traditional rule-based system was something that was signaled as a cut in the link. So we made our first steps on that. It was a system called Panama that was working on this, and it was our also training project for understanding how to introduce AI in the company. Another point that is in all the operator is very critical and is very keen to be exploited by artificial intelligence is the problem of energy consumption. A company like TIM, is using 2,000 gigawatts per hour per year of electric power. It's the second consumer of electric power after the Italian railway system. The same is in all the countries. If you go to Germany, to UK, to France, the telecom operators are the second source of consumption of electrical power. So every small improvement is important in this sense. Again, the use of the project we had was related to the fact of having a good matching between meteo forecast, traffic forecast, and conditioning and switching on and off elements in the network. It worked. It was again something that is not so maybe extraordinary from the point of view of idea, but it had a good return on investment in the project. It was mentioned there are much more forward-looking projects. For example, the point of digital twins and artificial intelligence are one of the key points of research, I think. Also, we are working a lot in Restart exactly for this. And one point is that, again, we need data and we need actionable data. So the point of having API and the way of interacting with devices, with the actual solution that are the network element, the devices in the network, will be the key point. This architecture, for example, of service management and orchestration that is called SMO by the Open RAN Alliance is something that we are looking very, very close to have these enablers in the network. I try to run a little bit to catch up also a little bit in time, but I think it was more to have an overview of the point.
Thanks a lot. And the last presentation of the session will be given by Aurora Terzani from NetReply.
Okay, I'll try to be quick, so we'll be in time. I'm representing here NetReply, that's a company into the Reply group. This was a video presentation, but I will give you some details to be quicker. So NetReply is a consulting company that works in the ICT industry, and we work to provide, aim to telco and enterprise market to use next generation networks. So we work in network softwareization, disaggregation. We participate in this program also in the cascade called Spoke 6. So a lot of things. Here, a quick map to explain who we are and what we do. And today, of course, we are going to focus on our work on data, AI, and machine learning. So the idea of today was to introduce you with some use cases, practical use cases that we worked on, and to show you the challenges of practical, real use cases. Most of the things were already said by the professor and Gabriele Liao's team. So let me spoiler already the final goal of this presentation. We need to cooperate. We need to bring AI into reality. We need to work together. In fact, as a first case, we worked on predictive maintenance problem. The predictive maintenance aimed to predict whether a device is going to fail, have a failure or not. What was the main issues we have working on this problem? Here, our customer was Vodafone Global, and even it's one of the major customers in the telco environment, we had a problem of data. We had incomplete data set. So what we did to bring real benefits to our customer, we tried to compare different approaches, predictive approaches, and worked with different data sets. So it's not easy. When we have to go into reality, it's not easy. We need data. We need to handle them. We need to manipulate them a lot to try to obtain something. So to show our customer the benefits, the real benefits of AI, we need to work a lot on data. So the first approach was a temporal shift. Another spoiler was the best one. And we compared this temporal shift approach with a temporal window. What we did was shift the value of the time series to create a multivariate time series as an input to an LSTM. In fact, another thing that we did, try different approaches, because again, when we go into real use cases, it's not more theory. We need to try, and we need to try a lot. So for this customer in particular, we obtained some result with the LSTM, was the best one. But I want you to notice, we had a good precision. That was a good thing, meaning that the algorithms was able to predict the fault, so good one. But what was the problem? The recall values. What does it mean? It means that we were not able, even if we were predicting well the failure, we weren't able to discover them all. Imagine do this in production. It's impossible because you are going to lose a lot of money, so our customer will not allow to do this. So, what we worked on. Another issue that we face is the lack of simulation environment. So if we want to apply AI and machine learning in the real project, we need environment. So what we try to do, in this case, we work with team. We create a simulation environment. There was a load balancer for session border controllers. So we built an event-driven network, so a network that was able to react to the event, to the triggers, based on event or on an observability platform. So we had to build like from scratch. I'll go quick to the point just to show you the results. So in these use cases that we have done, in a simulation environment, we were able to reduce by 50%, like the half, the licenses in use in one case. In another case, we were able to reach just a 20%, but was a good result. But please note one thing. The tables in the middle represent the situation where an operator manually assigned the number of licenses to the SBC. As we can see, the numbers are pretty much the same on what we obtain with the artificial intelligence. Is that a bad result? No. Why not? Because we are avoiding manual work. We are trying to automate as much as possible, and we were able to reach dynamic allocation. So imagine to have data. The first problem, the thing that I've said before, we need data. We need a lot of data to obtain these results. Because if we have just a subset of data as we did, we can achieve something and we can achieve it also manually. But if we want to do this dynamically, we need to have more data and continuous data. Again, another problem. I said, we miss simulation environment. First was quoted also by the professor, the digital twin, it's the key to work on networks. Why? Because a digital twin is able to replicate the complex environment of a network. And what we did, in this case, our customer is Terna. We wanted to work also not only on the supervised algorithms like we did before, but we tried a new approach, the reinforcement learning, because since I've already stressed a lot, we are missing data. The reinforcement learning is an approach that is able to work directly with the environment. So the data can be obtained like in the moment. So it's a good thing, and we don't need also to work on the storage and to maintenance of the data. We are working directly with the network. In this case, we use a deep queue reinforcement learning algorithm, and the use case was a routing optimization. I want you here to notice that the point is that if we use a digital twin and together with the reinforcement learning, this was just an example. We can use also to optimize different KPIs altogether. And if we imagine a NOC, operation center, like it was in this case, it's not one KPI at a time. It's a lot of KPIs all together that we have to keep in control. So our result was just a proof of concept. But again, my goal today is to highlight how it's important to cooperate together. with the university to study the effects that this algorithm, which are the best approaches that we can use into reality, but also with customers, telco operators like Tim before, because we need to work on real environment to really obtain the benefits that AI can do in a complex network. I'm talking a lot about data, and so far I've talked about networks data. But if we think to real cases, the network operators, the telecommunication environment, use not only traffic data, but also images. Why images? Video, for example. This was an example of a network cabinet. Our customer, in this case, was Vodafone UK. They need to automate the operation, the manual operation of going into a cabinet, taking a picture, extract the information of the picture, and then elaborate. In this case, we use the object detection and together with optical character recognition. The results were good, but guess what? We were missing data. So, sorry to stress this a lot, but this is a real problem. Another interesting thing that we are doing so far is working also with network operators for the security issues. Like imagining the cabinet I said before, also the problem of controlling and managing people accessing the cabinet. So in this case, we use the YOLO algorithm for people detection. And what I want to highlight here is this object that is called BoxNet. It's something that we are working on. That it's a really interesting experiment that we are carrying on to bring networks, AI at the edge. In this way, we are trying to work to bring the AI application, but also thanks leveraging on networks, we are bringing this like intelligence at the edge, close to the real needs, close to the problem. What are the next steps? This is something that we are working on. Open RAN. Open RAN, as the professor said before, it's part of the AI-based network. Here, notice, we are not talking about AI and networks, but networks, AI-based networks, sorry. So something now that is native for networks. So issues that we are meeting, we are encountering here at are the fact that we need to still work on the theory. Here, there's a lot of studies that universities are doing, so that's, again, something that I want to say today. We need to cooperate, because in this case, we need to find customer that needs these use cases, but we need the support of the university to work on theory, because here, it's all new. This was a use case also quoted by Gabriele Elia before, so it's true. Customers are working on this. Energy saving is really important. And this is something that we need to take care for sure in the telecommunication environment, but for everything. So that's something where the AI can really bring a benefit. And last but not least, generative AI. Guessing what? I used ChatGPT to work on this presentation. So it's true, it's real, it's something that everyone is using right now. So why not using this also in the telco environment? Why not using this also in the telecommunication? Where can we use generative AI? For example, in the development of all these applications, but also in the configuration of devices for the telco operator. So I try to be as quicker as possible, but just to summarize to all the takeaways. So AI and machine learning are really doing a difference for the telco operators. But what we have to do is taking care, it's consider that we need data, we need high quality data, and we need to have in mind solutions that can be easily adapted and integrated in different contexts to bring this into the real world. So, what are the next steps? Encourage, as we are doing today, the adoption of AI and machine learning into real use cases, but ensure also to have data, to have high quality data, to enable also the reliability of AI models. And as I said already a lot of times, but that's really important, we need to work together. Universities, telco operators, consulting company, and everyone. Why? Because in this way, we can really make a difference. And that was all. Thank you.
Thank you very much. And we will move now to session number 4, optical highways. So the first keynote presentation will be given by Piero Castoldi from Scuola Superiore Sant'Anna. Sorry. Indeed. And you have 25 minutes, including questions. So you can, okay, just to keep the time.
No, they are older than us, so yeah, good friends, definitely. We collaborate on many topics, but a nice start. So, thanks for the kind introduction. And so this talk, let's say it's around the findings we started having on Grand Challenge 18 on the optical highways. And we are going to explore some challenges that the optical networks and devices trying to give a response with this technological solution for 6G. Of course, when we talk about generally speaking, we talk about mobile radio, we think about wireless, but we have to remember that after the BTS, we have basically optical fibers and a lot of optics. And optics can be an answer to many problems, starting from power consumption. Photonic integrated devices are overcoming the problems of electro-optical conversion and offering many saves in terms of transmission power. Photonic integration is an answer to the miniaturization of devices and the challenges about programmability, because optics is great for transmission, a little bit less practical for processing. Optics is an answer to increasing bandwidth and also for offering solution on the aspects of security. And then, besides this, we have to solve the problems which are not a problem in the electrical domain, but they are in the optical domain, regarding agility and control of the optical channel that is time varying, going to the goal of zero touch of optical networks. So I'm not going to give a solution for everything, so I'm going to show you some the ecosystem that we are building in the Grand Challenge 18 among some projects that started joining this challenge. So everything starts around the structural project on optics regulator, and here I have presenting a view of where optics can play a role in the global connectivity scenario. Also with a view here on the objectives of what ITUT calls IMT 2030, that is basically 6G, starting from IMT Advanced, that is already beyond 5G. So these are the specs of the intermediate generation after 5G. And you see here that there are most goals are of an increase or a decrease of an order of magnitude in, for example, density of devices or energy consumption or peak data rate or user experience. Only mobility is a matter of doubling, but when we are about at 1,000 kilometers, this is enough. So going back to the scenario of the optical networking, on the access we do have all the problems of BTS disaggregation, so functions which are shifted from the BTS to distributed unit and centralized units. And here also the decommissioning of copper towards fibers. And so here we have some response from low energy photonic integrated circuits. In the middle, we have capacity scaling for all systems supported by optics. And of course, on top of that, the monitoring level that is peculiar of optics, because the optic channel is very variable compared to the electrical wired, and then the orchestration and high-level control. Not forgetting that networks of the future will include a computing element close or far from the user in edge or far data center. So helping on this, we do have focus project, graphics for the access, LAN for other technologies. EPIC is a transversal project innovating in peak fabrication, SensingNet working on joint communication and sensing, and some attachment also coming from the optics channel towards non-terrestrial network, and the super project on orchestration that is a general umbrella for all these kind of problems. So here, not pretending to be exhaustive, so what the technologies are bringing for what KPI, or key VI, so let's consider both performance and key value indicators. And these are the technologies that we have considered as important at the data plane or the control plane, and which are bringing different benefits from capacity, latency, and so on, in order to meet the new requirements of IMT 2030. So there is a lot of work possible and ongoing, and we'll see some of the directions that are taken in restart in this towards these goals. So let me first start mentioning about what levels of energy optimization we can achieve on network reconfiguration. So optics has this kind of double level of logical links and light paths supporting data. So for example, if we have heterogeneous initial routing with two light paths supporting two requests, we can do green reconfiguration by grooming the connection on a single light path. And you see here that we are significantly reducing the number of transponders, so the green triangles, which consume a lot of power. Or we can keep the two light paths, but we consider a bypass of the intermediate node, reducing still less the number of transponders, but maybe using a lower modulation format which consumes less power. Other performance improvement comes, for example, from the hybrid integration, where you see here we can put on top of an electrical controller the optical modulator, and so we do what is called the flip chip. So we just put and solder it, other performance improvement with a look at what can be done in the processing in the network comes from the optical processors, especially for linear operation. You see here an architecture where you have elements for through and drop and a kernel that is a processor, and with proper coupling you can do several operation or shifting several operation of linear processing at time of flight. So processing time, it is just the transit of the signal, no delay at all. Another area of interest is about microwave photonics. This has been commented a lot also in previous talk. So here the focus is about just presenting two ideas for the optical beamforming. Beamforming is a complex technique that also has to keep into account the fact that you don't want the beams to squint, so to have to be very stable, and through time delay beamforming is exactly in this direction. Another problem is both at the physical layer and at the protocol layer, the problem of flexible functional split of the functions that originally were totally on top of the base stations, and now with the different release of 4G and 5G are proposing different splits of the functions between the distributed unit and the centralized unit. As an extreme, functional split is when you just leave the physical function on top of the BTS and do a complete offloading of the logical and protocol operation in the centralized unit. And this is one of the area of study that are part of the grand challenge. Also, Li-Fi is the potential substitute or Wi-Fi in certain environment and for certain application. You know that there are already implementations, especially using infrared, but the challenge is to embed it in natural light. So, for example, white source or visible light. And here there is, for example, this study that is conducted in collaboration between the Scuola Sant'Anna and CNR on a very simple approach where the focus is basically on the download, because the download is from for example, the lightning towards your laptop, and this is quite critical unless you have a collecting surface that is sufficient to collect enough energy. So the key attention is about a concentration device that is being studied as something that you can put on one side of your free surface on your laptop, that is this red device, and it has already been tested with very simple and commercial modules to reach already, totally embedded in natural light, speeds of 10 megabit per second, sufficient, for example, for a video distribution. Of course, these experiment are totally at the physical layer, so they goes with the speed of Ethernet, so it is totally cabled, for example, on the Manchester encoding of the 10 megabit Ethernet, and can be embedded also on the different Manchester encoding of 100 megabit per second in the future. just to give an overview of what is the process adopted for photonic fabrication in this grand challenge. So I have here highlighted from the the theoretical study of the circuits up to the system level, up to the PDK that go to the foundry, and this phase can be supported by the focus project HEPIC up to the middle of the design, to the foundry, to the packaging, to the characterization, and up to the use case. So currently, in the middle of the project, for many devices, we are here, and we are confident also that with the help of EPIC, we can bring several devices at the end of the project towards the enhanced TRL, that is having the device actually available. Another interesting area of research in optics is the physical layer security. Of course, a lot has been said about QKD, and we have QKD, but for today I wanted to focus on a different idea, that is the idea of optical fingerprint of devices. Basically, by measuring Rayleigh scattering of pigtails or short devices, you can characterize an optical device with a random fingerprint that comes from the manufacturing process. And you can use this fingerprint as the security key. So you measure it, you give it to the device you want to authenticate, and then with this authentication, the device is enabled or not enabled to operate on that specific optical device. And of course, this serves for authentication, but also it can be used also to detect attempt of tampering or attempt of eavesdropping, because if there is a tap of power or a different optical channel, then the fingerprint is going to change somehow, and then the device is not more authenticated. That means it's not safe to attach to that pigtail because something wrong has happened. Another area of interest is about the capacity scaling, and the most notable technology for capacity scaling, the medium term is multi-band, so enlarging the third window of transmission, not reported here. I mean, there is a lot of literature, but I wanted to focus more on the long term. That is space division multiplexing, so using multi-core fibers. That is a compact way of just the multiplication of fibers. So fibers with many cores, and with this type of course, besides the problem of transmission and characterization, mode coupling, and many others, you also and we also are focusing on the way we can do software-defined control of such multi-core fiber, including the distribution of the key for security. Going towards the end of my talk, the area of monitoring is another important area in optical networks. Monitoring is necessary because all the reconfiguration or the new setup of a light path in an optical network brings perturbation to the others, the less or the more, but it's going to bring perturbation. But not only because of this, but because the network devices are more and more disaggregated. So they are not monolithic anymore, but they are composed of several devices which are specialized with different functions. So for example, a reconfigurable optical add-and-drop multiplexer can be composed of different devices specialized in their function. The same color indicates the same link that you have here, and you can compose an optical add-and-drop multiplexer in this way. Having a model for that translates into basically a digital twin is going to give you a real-time copy of your optical network and predict and support also with AI algorithm what could be the future and the forthcoming events in your network. Another technology I want to mention, because it's very recent, comes from OFC just last March, is about data processing unit. Data processing unit are a novel generation of network interface cards that are equipped with GPU, so they have a strong processing capability. They were thought only for electrical networks, but progressively they are supporting pluggable transceiver. These kind of pluggable transceivers are nothing more than transceivers, optical coherent transceivers. So they can support a reasonably long span of a few kilometers. And on the long term, a DPU with an enormous computing capability can substitute at the same time an aggregation router, a transponder, and a router in a single card that plugged inside a commodity server, as you can see here, can offload the server from all the typical functions of cybersecurity and just leave the server working on the networking function, because all the packet inspection can be done inside the smart NIC itself. So the edge load is reduced because the typical, let's say, monitoring function are directly done inside the DPU. So let me mention that in the session we are going to have two talks coming from the F-Project F5 graphics on the future optical active splitter based on graphene for next generation optical access. And I deliberately not spent a lot of time on the control plane because there is a specific talk on what control plane for optical network based on the AI will be and what are the findings so far. So let me acknowledge all the work package leaders and the PI of the projects from which I had contributions for this talk, and also take just a few seconds to make an advertisement about forthcoming events with Restart presence in Pisa, Frankfurt, and in Rome in the next autumn, with dedicated events in all these conferences. So thank you for the attention.
Thank you very much. So the next presentation will be given by Maurizio Casalino from CNR ISASI.
Okay, good afternoon to everyone. I'm delighted to present a graphics project. The extended title is Graphene Hydrogenated Amorphous Silicon Photonic Integrated Circuit Switch. In this project are involved 4 partners: the engineering department of the University Federico II in Naples, to which Professor Della Corte is the principal investigator and belongs to the engineering department of Federico II. Then we have the Institute of Applied Science and Intelligence Systems of the Research National Council. It is my institute. And then we have a company, Open Fiber, it's a leader in telecommunication. And finally, we have the engineering department of the University Mediterranea of Reggio Calabria. The objective of the project is to develop a photonic integrated circuit working as an optical router to be employed in passive optical networks. I'm sure you know what is a passive optical networks. We can say that nowadays this the most successful broadband access architecture for fiber to the home applications. At the beginning of the chain, we have some optical line terminal localized in the central office of the service provider. At the end of the chain, we have the user. In the middle, we have a network of fiber optics and passive optical splitter. We have two levels of passive optical splitter: primary flexibility point and secondary flexibility point. The secondary flexibility point is the patch cabinet we can find along the sidewalk of our towns. This is a picture of the cabinet, and we have also a scheme. At the input, we have the signal of the service provider. At the output, we have the users. In the middle, here, we have a permutation area. When a new subscriber is added, or an old subscriber that decides to change the service provider, it's needed that a technician goes to the patch cabinet and physically connect the service provider with the user in order to establish an optical link. The aim of graphics is to develop an optical router able to establish this optical link, but remotely, and of course in a reconfigurable way. Of course, this optical router should be also low power, broadband, low cost, everything. And of course, the advantages are clear in terms of cost, time, potential human errors, downtime, safety, expertise requirement. I don't know you, but I wouldn't put my hands in that cabinet because one mistake and crash all the network of the district. And this kind of optical router could be realized by considering a combination of 1x2 switches, of course. And we want to realize this switch, integrated switch in silicon, but taking advantage also on emerging material like graphene and hydrogenated amorphous silicon. Switches should be based on waveguides, which are single mode polarization independent, wavelength independent in the range 1310, 1620, because these are open fiber requirements. Moreover, this is an active switch. We need electrical power, but in that cabinet we don't have electrical energy, and we have to think some self-biasing approach. I'm going to present our results starting from this last point. We use a power over fiber approach. We dedicate one fiber to the optical power, which can be converted into an electrical power. And of course, we purchase a photodiode. We have characterized this photodiode in terms of wavelength, in terms of power. We perform some fitting operation in order to extract an analytical formula able to predict the current photogenerated by our photodetector as a function of the power and as a function of the wavelength. After that, by this photodiode, we are able to create a voltage. This voltage needs to be stabilized. We use a DC-DC converter. We have assembled this system. This is the power unit, for instance, for our microcontroller, able to change the configuration of the optical router. Optical router is based, the switches, 1x2 switches are based on waveguides. We realize waveguides starting from a silicon on insulator substrates, and then we use hydrogenated amorphous silicon, which represents the rib of our waveguides. Of course, we have optimized by numerical simulation, by using a numerical tool, the geometry of the waveguide in order to make the waveguide single mode polarization independent. We have realized in our clean room these waveguides by depositing hydrogenated amorphous silicon on top of silicon. We etch hydrogenated amorphous silicon. The etching process is a little bit challenging because we need to get really sharp sidewall. And of course, we tune the reactive ion etching process in our clean room. And now, this is the waveguide we use for our switch, but I would like to show the role of graphene. Actually, we don't work with graphene, but we work with graphene insulator graphene systems. It's a sort of graphene capacitance. It's well known that when you change the voltage on the capacitance, you can change the graphene Fermi level. and you can change the graphene refractive index. If the system, graphene capacitance, is introduced in your waveguides, you can change the effective refractive index of your waveguides. And many colleagues, many people, many scientists place graphene on top of the RIB waveguide here. But you can see that the maximum of the optical field is not overlapped to graphene. Graphene interact only with the evanescent film. Our idea, and this is the main idea, is to place graphene in the middle of the cavity. This is because we use hydrogenated amorphous silicon. We place graphene where the excited mode has its maximum value in order to make the light-matter interaction stronger and in order to increase the variation of the effective refractive index of our waveguides. Of course, it's possible also to change the absorbance of graphene by applying a voltage to make more or less absorbing, to make graphene almost transparent, and so on. Okay, this is a good idea, but we have to place graphene in the middle of our waveguides. It's not very easy because graphene, we use a single layer graphene. The thickness is the diameter of a carbon atom, and we have to deposit on top of graphene hydrogenated amorphous silicon some 100 nanometer of hydrogenated amorphous silicon. We take the risk to destroy graphene, we take the risk to damage graphene, but we discovered that by depositing hydrogenated amorphous silicon on graphene in our clean room by using a plasma-enhanced chemical vapor deposition system at a temperature of 1 degree, we are able to transfer hydrogenated amorphous silicon on graphene without damaging graphene, without destroying graphene, as confirmed by the Raman analysis. So, okay, now these are our first preliminary results. Now I can start walking about switch. We have took in consideration many configurations for our switches. We perform numerical simulation also with the numerical, starting from microring resonator. I'm sure you know what is a microring resonator. It is constituted by a ring structure and two street waveguides. Of course, it works generally employed as a filter, but it can be also employed as a 1x2 switch. This is the input port. We have the output port 1, and we have the output port 2. At resonance wavelength, light coupled in the ring structure, and of course, you have the most part of the power in port 2, low power in port 1. It is described by this graph. Of course, if we include graphene in the ring structure and we change the voltage on graphene, we change the refractive index of the ring structure, and we go out of the resonance. In this case, the most part of the power will go to port 1, low power in port 2. This is described by this graph. You can see that at minus 10 volt, the most part of the power is in port 2, but at already 6 volt, the most part of the power is in port 1. It works as a switch, but there is a big problem. This structure is based on interference phenomena, of course, and it results really highly sensitive, dependent on the wavelength, and this doesn't match with the open fiber requirement. A second switch we took into consideration was based on Mach-Zehnder interferometer, a Mach-Zehnder interferometer-based which is constituted by two-directional coupler, by two waveguide arms. One of these arms is provided of a phase shifter, of course. When no shift is applied to arm 1, the light from input 1 goes to output 2, a light from input 2 goes to output 1, we are in cross state. But when a pi Greco phase shift is applied on the arm 1, input 1 goes to output 1, and input 2 goes to output 2, and we are bar state. We try to simulate the phase shifter by considering graphene embedded between crystalline and amorphous silicon, but the structure resulted very, very long. We have problems about concerning losses. Moreover, also in this case, this device results really wavelength sensitive, and so doesn't match with the open fiber requirement. This is a third switch we have simulated. It is an adiabatic switch. Adiabatic switch is based on a taper waveguides. A taper waveguide is a waveguide whose cross-section changes, but slowly changes. More in detail, we have an input waveguide with a constant cross-section connected to a central taper waveguide whose cross-section reduces. On both sides, we have two taper waveguides whose cross-section increases, and then two S-banded waveguides. The working principle is very simple. When light propagates in the central taper waveguide, cross-section area reduces, refractive index, effective refractive index reduces. At the same time, effective refractive index of two taper waveguide, two lateral taper waveguide increases, and slowly, adiabatically, power can be transferred from the central taper waveguide to lateral taper waveguides. This is a splitter. We split the power into equal parts. Of course, in this case, no interference phenomena are involved, and so we can say that this switch, we expect for this switch, wavelength and polarization dependence is really lower. Moreover, from a technological point of view, from a point of view of fabrication, it's certainly easier to realize this kind of device with respect to ring resonator. We have simulated a splitter, first of all, symmetric Y splitter, basic on adiabatic structure. We have optimized it. The optimization process is not very simple because many parameters are involved. The length of the taper waveguide, the gap between two taper, and also the thickness of the silicon rib waveguides. But you can see that after the optimization process, this work as a splitter in both T and TM polarization. It is not a switch, it is a splitter. But if we increase the refractive index of the upper waveguides, for instance, by an increment of 0.0025, in T mode we are able to address the most fast of the power in port 3, low power in port 2. This is the length of the taper waveguide. We can say that the higher the length of the taper waveguide, the higher the difference between the power into port. Unfortunately, it works only in T mode, in T polarization, but not in TM. After a further optimization process, we discovered that if we increase the thickness of the silicon rib waveguides, we have a switch behavior in both TM and T modes. We reach a certain independence of the polarization. We investigated also dependence of the wavelength. In T polarizations, which are wavelength insensitive. In TM, we have a slight dependence of the wavelength, but we can say that the shorter the wavelength, the higher the power difference between two ports. These last two graphs on the bottom are in order to show that the greater the difference in the refractive index between two taper waveguides, the greater the power difference between two ports. In previously example, we consider an increment of 0.0025, in this case 0.01. And so, we try to simulate also adiabatic switches, but based on relaxed sides, relaxed dimension, in the micron range. Because this amplifies the fabrication process, of course. It's possible to realize more relaxed adiabatic switches, also getting polarization independence, but to be honest, the device results very, very long, and we have problem about losses. Probably this issue deserve more investigation. So I can conclude. Of course, okay, this is a message to take home. I would like to thank Professor Francesco Della Corte, who is the principal investigator of this project, and of course all my colleagues collaborating to the activity, in particular colleague Teresa Crisci, and of course all of you for interest and attention. Thank you so much.
Thank you very much. We have time for one very short question.
Thank you. Very interesting talk. It's more a comment than a question. If I understood correctly, you have this photodiode that acts as a power supply for your entire switch. Why don't you use graphene itself? I mean, another part, let's say, not the modulator, but a graphene photodetectors online on the same chip just to create a photovoltage to drive your modulator?
Yeah, this is a good question. For question of money, because it's easier, of course, to buy a photodiode working at 1,300 110, we developed the project by considering this a second aspect. The power unit for us is a secondary aspect, a secondary issue, of course. But I have to say, okay, this is a good idea. We have developed a photodiode based on this structure with graphene embedded between crystalline and amorphous silicon, working at 1.55 micrometer with 1 ampere on watt of responsivity. This is absolutely possible. Good idea. Thank you so much.
Thank you very much. Let's thank the speaker again. And the last speaker of this session 4 is Mem Ibrahimi from Politecnico di Milano.
Thank you. My name is Mehmet. I'm with Politecnico di Milano. I'm an RTDA working in the Rigoletto project. The purpose of this talk is to show a successful implementation of a large language model pipeline, and also to make a case that hollow core networks is the next technological breakthrough in optical networks. So even though my slides apparently mismatched for some reason, so I'll jump straight to the first topic. It's very much in line with what has been discussed since lunchtime. I'll go back in time in the 1980s when the concept of expert systems was very, very popular. The definition of expert systems is that they're an intelligent computer program that allows to solve problems that are difficult enough that they need expertise. So basically the idea is that you get an expert that allows to build a knowledge base and create a set of rules engine so that you can have a user, a generalist, which is a non-expert, that is able through a user interface to query and then get advice from this system. Nowadays, we are in the age of LLMs, as was discussed before, and we have the possibility of typing some requests to the ChatGPT and get some advice. What are LLMs? In the most simplest terms, we can say that they are nothing more than next token predictors. Basically, the idea is that given a sentence, the LLM allows to predict the next word. So in this particular example, we have the quick brown fox jumps over the, and the LLM can predict that the correct way to end the sentence is, say, through over the lazy dog. Yeah. So what does LLM have to do with optical networks anyway? At Polymi, we have a testbed which is able to be configured, but only through REST APIs. And we have this course called Lab Experience, and students have to come and learn how to use this testbed. Of course, it takes time for the students to learn how to use the testbed. So the idea started as an exercise to build a tool, an interface, that allows natural language to configure a network. So the question that we posed is if we can use LLM to translate natural language intents to some data structure. And I think a very fair question would be of what is the objective of using LLM. As my slides are messed up, there is supposed to be that it's an instrument that takes a generalist from 0 to average. I mean, what does it mean to be average? Because I think what is important to understand is that LLM will not substitute experts. Rather than will take somebody who's a generalist from 0 to average. And to put it in simple terms, if we use the example of primary school students, would be like getting a 6 in the pagella. So you get a passing grade. However, to use LLMs, you need to know how LLMs work, and you also need to understand how optical networks work. And the main challenges that are needed to be addressed is the fact that LLMs know nothing about how to control an optical network, and they tend to hallucinate, to generate content which is not appropriate, let's say. And there's many ways of doing it. We went the cheap way, which means we used in-context learning, which basically means that all the relevant information is given in the prompt. Here I'm just flashing an example of the GitHub page that will be made publicly available. And we used compositional learning and constraint generation. The idea is that LLMs tend to hallucinate. So you want to make sure that whatever they are generating can be controlled and can make sense to whatever controller is being used for configuring the optical networks. And without getting too much into the ins and outs of what happened behind the scene, let's say, this is an overall idea of the pipeline that we built. So we have the actual testbed, which is controlled through some RESTconf SDN controller, which is proprietary. And on top of it, we put the LLM pipeline in a way that it generates some data structure that allows to then configure the network. Does it work? We used an open source LLM. In order to test and to see if it actually works, we had to manually curate some data set. We identified 3 tasks, so generating a light path, a service, and measurements. The problem of LLMs is that there's no baseline, so we had to come up with a baseline as well. The baseline was using in-context learning, but without the part on the constraint generation. And how do you measure if it's good or not? So we checked how many times does the LLM make mistakes. And we identified basically the number of times or the types of mistakes that the LLM can make. For example, generate a structure which is not compliant, which is not adjacent, or missing a task. You ask it to generate the light path and a service, and it does not do that. Or more frequently, the fact that it tends to hallucinate and create more than it should. And here I'm showing some numerical results. On the bottom, on the x-axis, you see the type of metrics that I just explained now. On the left y-axis, you see the number of errors, and on the right y-axis, you see the cumulative error rate. You see that in most cases, besides the first one on the missing requirements, our approach beats the baseline as somewhat intuitively expected. But what is important, I think, to emphasize is the fact that if we check the cumulative error rate, we see that our proposed approach has a cumulative error rate of around 20%, whereas the baseline goes over 90%. What are the lessons to take home? The fact that in order to implement an LLM to configure successfully an optical network, you need to know how the LLMs work and also how optical networks work. The problems are many. The fact that there's no established benchmarks. The fact that it's very difficult to know how to evaluate the performance of an LLM. One idea is LLM as a judge, so you pay a lot of money so that you have a very powerful LLM which can serve as a judge to whatever you implemented. And there's obvious concerns on scalability, and there's always a need for some manually curated data sets. But we're moving forward, and we are bringing this solution also to an industrial testbed. So we are currently, this is an ongoing quest, let's say, that we have. So in the remaining 5 minutes, I want to focus on the second part, which is on hollow core fiber networks. I want to somehow do a historical tale of how optical networks have evolved. So since the 70s up to today, the standard single mode fiber is what's being used and allows to provide a lot of capacity, no? And as Piero anticipated, somewhat since the 2000s, there's been an increase in the deployment of fibers. There's been a lot of work on multi-band networks. And there's also a lot of work being done on multi-core fiber networks. So it's very obvious that the future of optical networks is parallel. And this somewhat resembles a highway of cars, no? But in a highway of cars, the leftmost lane is the fastest one. So our leftmost lane is hollow core networks, which basically uses, without going too much into the detail, uses air as a transmission medium instead of glass. There's been a lot of research ever since the early 2000s. There's been more advancement since the 2018 onwards. And to make a point that this is not just some cool idea, I want to make a point that Microsoft actually acquired the company, which is known as the top company for producing hollow core networks. What are the actual benefits of using hollow core networks. So to put it simply, it provides lower propagation latency. It has better properties in terms of nonlinear effects, and it has a very low transmission loss. So here I'm showing an example of a simple optical networks composed of some nodes, some data centers, and some clients. If we introduce hollow core fibers, we are able to reduce the number of the edge data centers, because the number of data centers with the increase of the data is obviously going with that trend, basically. And just introducing a hollow core fiber budget of 20 allows to reduce significantly the number of edge data centers. Without going on what we did, because just to give you a brief idea, we did what we are known for as a group. We developed some optimization tool to minimize the number of edge data centers. And just to provide you some results, here I'm showing a case of over a realistic 52-node network. On the y-axis, you see the number of data centers, and on the x-axis, you see the latency, which varies between 100 and 400. And you see that in the case when there's no hollow core fiber, you have a certain number of data centers. And as you continue to deploy hollow core fiber, the number of data centers reduces. We see that we have a reduction of around 30% of edge data centers by just upgrading around 24% of the links with hollow core fiber. Jumping forward, the lessons learned are that hollow core fibers are extremely beneficial for low latency applications. They enable capacity scaling for next generation optical networks. Remaining challenges are the fact that there's no mass production, there's no guidance on how to deploy them. It's not very clear how it will age because it's been very recent. And it's not clear how amplification over a very wide band will work. Moving forward, we are currently working on also energy consumption using hollow core fiber. I also wanted to use this platform to somehow call for merging of energies and say that I think hollow core is where the wireless and the optical can also meet. I see a lot of, I see less synergy, let's say, on the group that work on optical and the ones that work on wireless. I think this can actually enable the fact that using hollow core in front haul can really move forward. So thanks for the attention, and thanks to my team.
Okay, with a certain degree of modesty, I retitled this talk in Integrating Sensing and Communications. And the talk, as you know, is divided into 3 segments. The first delivered by myself, the second by Marco Manzoni from Politecnico di Milano, the third from Egidio Aragonese from University of Catania. Well, you know, probably let me refresh your memory, that the project I will be talking about is titled Integrated Sensing and Communications for a Greener Environment, is a cage. I must say that never in my life would I have thought that such an acronym was so appropriate given the enormous number of constraints we have to comply with. But anyway, you can read it also with an Italian pronunciation, Isacage. And of course it is, as the constituent words say, a project about joint or integrated communication and sensing. And you know that JSAC, or ISAC, as you want to call it, has a kind of long history, because the first idea of this convergence between communications and radar came out back in the 40s by Stockman. Of course, at the time there was no cellular system, so there was no point in imagining communication-enabled sensing, but he proposed a radar-enabled communication system, namely to exploit radar returns in order to establish communication links. After that, the topic slept for a long time until the scaling up of the carrier frequencies of wireless networks, induced, of course, by the need for larger and larger bandwidth, made them invade those frequencies which are traditionally assigned to sensing. And as a consequence, the issue of a compatibility, of a negotiation, of I would say, a coexistence arose. And I would say, I would date to the early 10s, the moment when people started to recognize that coexistence was an issue, and that somehow some countermeasures to the mutual interference between active architectures insisting on the same portion of the spectrum had to be taken. From there, of course, we have had a number of developments, primarily, let's say, starting in 2016, if I am not recognizing the efforts of someone in the audience, I beg his pardon. But at best of my knowledge, we got sensing through communication signals, and this was fostered by the widespread usage of millimeter wave communications. You know that millimeter wave communications, well, they rely mostly on line of sight connections, which are reminiscent of radar operations. They require beam alignment and beam tracking procedures, which are reminiscent of target tracking and target detection. After that, I would say at the same time, the idea of DFRC, dual function radar communication, arose, which means that radar and communications were thought of as a kind of holistic system to be designed together with a unique transmit platform and with multiple functions undertaken on that platform. Of course, this is a very impactful solution, but at the end of the day, it was always radar-centric, as far as I know. Namely, I have always seen a radar modified in order to accommodate typically low-rate communications than the other way around. After that, we have had this kind of triumph of Isaac, wherein we have this joint design. It could be communication-centric, where we have a basic communication system with a functional adaptation to sensing functions, a basic radar system with some adaptation to communication function, or a totally new, very impactful approach, wherein the two functions have equal dignity at the design level. And finally, there is, for the future, the idea of Isaac networks. Well, I hope, how long did I speak? Anyway, whatever. What is Isaac Age about? Well, Isaac Age relies on two basic pillars that I would define: physical integration and functional integration. In physical integration, we have two active transmitters. One is a radar transmitter or a sensing transmitter, or call it whatever you want to call it. The other one is a communication transmitter. And in that case, we have a coexistence problem, which does not have much impact on the existing infrastructure. It's an infrastructure preserving approach, but of course requires some effort. At least it requires, if no form of cooperation is foreseen, it requires some interference mitigation procedures to be undertaken at the respective receivers. Or in a more ambitious framework, we have, of course, to go to cooperative system, which means that the probing signal of the of the sensing system and the code book of the communication system are jointly designed, of course, with a large amount of cognition. Here, for these two approaches, I would say that, especially for the second, a key tool is, of course, waveform design. which was mentioned by Umberto this morning, of course, we can do a lot of waveform design. Typically, waveforms are designed with some constraints, rigorously non-convex, and of course, we can end up with having algorithms in order to have optimized waveforms. Then we have a functional integration. Here I call it functional because there is no interference generated whatsoever. We may have, everything is Isaac, but if you want to introduce a little bit more precise taxonomy, we could say that we may undertake opportunistic sensing, which means using communication signals in order to undertake sensing. All these topics are being explored, of course, in Isaac Age. And here, as I was mentioning this morning, well, the waveform design idea is taken off the table. We have to make the most of the signals we have. Excuse me, you are following me with this camera. I don't know, I don't want to be recorded. Anyway, did I sign something about recording me? I'm not sure. Look, I can't say like this. Anyway, okay, I'm gonna say like this. So, as I was saying, the major tool for granting a good performance, good sensing performance, which is away from the design, is taken out of the table. But and on top of that, we have the famous, more or less famous, random deterministic trade-off. Communication waveforms are random. They could be de-randomized if the receiver is collocated with the transmitter and has knowledge on the transmitted data, but of course, we can't choose the code. We can't choose the data stream. We can't choose the preamble. We can't choose anything. Even though I must say that Marco will be illustrating something on this matter right after my talk, there are people who are thinking of slightly modifying the communication transmitter waveforms in order to confer a large amount of resilience once it comes to sensing. Then we have opportunistic communications. These are typically communications which use the radar signal and the radar scattering as an ambient signal in order to grant some low-rate communications. This has been studied in the course of Isaac Age. And at the end of the day, what comes out is that for low-rate communications, and in the framework of ambient backscatter communication, things theoretically work. I underline theoretically because, I mean, no experiment has been so far undertaken. And here is where, more or less, Isaac Age stops. With all these topics are covered, and in the next talks, you will be also seeing some results, not all the results, a couple of results. And then we have fully integrated system, as I was saying, which is a research topic. We are kind of at the border of fully integrated system, but we will be reverting to this point later on. Not too much later on, because I don't want to test your resilience beyond reasonable. Okay. Now, I would like to illustrate a little bit what's next. And for this, I would encourage you to have a look, for those who are interested, to a recent paper co-authored by Natalia Gonzalez-Prelcic, a number of people, and Davide Dardari also, which somehow gives a vision of what is going to be a communication-centric, in my mind, approach to an Isaac network. Well, communication-centric means that they always start from the point of view of communications and accommodate sensing, even if with some functional modification. And well, the key requisite, the key functions that could be required of future ISAC networks are high accuracy positioning. There is an interesting distinction between positioning, which is for active users, and localization, which means detection and state estimation of non-radiating objects, of scattering objects, and imaging, of course. Then, of course, some typical sensing services, intrusion detection, and so on. And finally, an effort to assist the communication functions through sensing. And the building block, the characteristics that these could rely upon are some fundamental characteristics, which is the diversity and the heterogeneity of the information source. And there is a transparent reference to reconfigurable intelligent surfaces. Now I must say, you know what they are. They are programmable mirrors, nearly passive or with low consumption, which refocus the impinging rays in a given point of the space. Now, while in communications, RIS have nothing to demonstrate, I would say, for sensing, ISAC Age is wondering a lot whether they are useful, marginally useful, or sometimes damaging. Why? Because I do not want to enter the discussion, but we are holding a lot of meeting about this point. We have undertaken a number of studies on the potentials of RIS in radar sensing. And the idea is that when it comes to detection estimation, an unknown number of objects of unknown state, which are possibly range spread, because at millimeter waves, the bandwidth is in the order of gigahertz and the resolution is in the order of decimeters. Well, and also in the presence of reverberation, which is clutter, which undergoes the same magnification effect as the useful signal, well, it is questionable whether an RIS brings an advantage or not. We are still studying on that. Then, okay, of course, as further characteristic, we have sensor diversity, so the importance of data fusion, and learning capability, which is somehow combine data and new observations, of course, in order to come up with an adaptation to possibly changing environment. Let me say that, let me give you an idea of a little step forward that some people are thinking of taking. Namely, let's lift the eyes a little bit on the idea of total preservation of the existing infrastructure. Now let's try to see what we could conceive in a fully ISAC design, which somehow allows us to change the transmitter structures and also the operation of the decision circuits. Well, these ideas I'm putting forth came out during a research meeting with a company whose name I'm not authorized to disclose. I don't know why. But anyway, the idea that came out from this discussion is that we may think, when designing the system, of two basic scenarios. ISAC 1 focus on target detection. What is a target? Given a scene, any scene, a target is a new object, whatever kind of object, which enters the scene and eventually may leave it. Okay? This is a target. A transient phenomenon in a stationary scene. Well, And then here you have a number of examples, all these figures of these slides. The slide is not mine, of course, because I'm not so good at making slides. Anyway, what are the key metrics that we have to use in this case? The key metrics are those typical of radar systems. No escape from that, which means maximum detection distance and accuracy, which is detection rate and false alarm rate. We can't afford an explosion of false alarm when it comes to surveillance. Think of Ukraine, okay? Then precision, then classification accuracy, and so on. But these are some figure of merit that somehow should enter in the project of the system, in ISAC 1. Then we have ISAC 2, what they call ISAC 2. ISAC 2 is much more akin to the world of communication people. You know, there has been, during the development of this project, an effort, my opinion successful, to conjugate two different languages, two different lexicon, communication mentality and radar mentality. Radar people typically think that communication people make unrealistic assumptions. Communication people think that radar people don't know information theory. So at some point there is, let's say, a dichotomy between these two communities. And one of the merits of ISAC is that it is somehow closing the gap which has long separated the communities. Well, here we have ISAC 2, which real-time environment reconstruction, of course with an eye kept to assisting communications in order to get as close as possible to the capacity. Well, if the capacity is that one, it depends on the type of channel, of course. And, of course, we have that, to this end, and then on a parallel track, we have somehow a reconstruction of the surrounding environment, which means getting spatial information and also going up to somehow attribute determination, which means classification of the material and so on. And the key technologies, the key technical challenges that during this meeting emerged were, first of all, starting with enhancing the sensing capability of a single site, whatever is the site, through the traditional tools that we have seen so far, which is waveform design, RIS, wherever applicable, and so on. Then go to multi-site data file fusion, which is somehow a form of angular diversity, which may allow us to end up with, I'm done, 20 minutes, I'm sorry, end up with better precision, and finally collaborative sensing, wherein the active devices undertake collaborative sensing, which means a large degree of coherence and so on. Well, I think I am done. I can leave the floor to Marco Manzoni for the next talk, and I thank you for your patience.
Thank you. So Marco, is your time now. Marco is from Politecnico di Milano. Marco Manzoni.
Hai fatto.
Okay, so thank you. Thank you, Marco, for the introduction. Thank you, Umberto, for the introduction. So I'm Marco Manzoni, and I work at Politecnico di Milano. My main research interest is about radars. But actually today I would like to talk about 4 research strands in integrated communication and sensing from the, let's say, from the ground level to the stratosphere. Actually, the first topic will be waveform design for integrated communication and imaging, so it's like platform agnostic. It works whatever the platform. And then I will talk about the cooperative and coherent multistatic imaging in automotive scenarios. So we will stay on the ground, let's say. And then we will step up a notch and talk about UAV-based synthetic aperture radar using OFDM signals. And then we will step up a notch again, quite a bit actually, going in the stratosphere to like 20 kilometers, talking about high altitude platform station for simultaneous network offloading and extended scene imaging. So let's start from COSMIC. COSMIC is a fancy name, stands for Connectivity-Oriented Sensing Methods for Imaging and Communication, and it's basically a waveform design algorithm. The scenario is the one that is depicted in this figure. So let's imagine there is an entity. This entity can be whatever, can be a vehicle, a UAV, a base station, whatever, that is equipped with a MIMO, ISAC or RADCOM device. And this MIMO device has like N antennas. These N antennas transmit waveform to illuminate the scene. And then there are M antennas receiving the echo coming from the scene. And this waveform needs to transmit information. They must carry information to another entity in the scene. And the echo that comes back is recorded by the M antennas. And after a processing called focusing, you can generate a radio image of the environment. Later on, when we will talk about UAVs, we will see what is actually a radio image of the environment and what I mean by integrated imaging and communication and not integrated sensing and communication. The key point about COSMIC is that the field of view is limited. So our scenario is like, I don't know, 100, 200 meters in distance. Like we worked quite a lot in the past with automotive industries, and we know that in automotive radar, they want like a range of 200 meters, 100, 200, maximum 300. Really a key point for this algorithm. So these waveforms are these N waveforms for the N transmitting antennas are all transmitted simultaneously, so in the same time window and on the same frequency. But they must be orthogonal. And what do I mean by orthogonal? Well, when I transmit like N waveforms, they are all recorded by the M antennas, and I must be able, at each of the M antennas, receiving antennas, I must be able to distinguish the contribution of all the N transmitted waveforms. And therefore, the waveforms must be orthogonal. And it means that I transmit like S1, and at the receiver, I do like a pulse compression, also called matched filtering, also called autocorrelation or whatever, depending on the field. And I want to cancel all the contribution, for example, coming from S2, S3, S4, Sn. And if I make the pulse compression with S1, I want just the contribution of the first transmitting antenna. And then if I make the pulse compression with S2, I want that everything is zero, so all the cross correlations are zeros, apart from that coming from S2. So imagine that there is just a point target in the scene. In the first plot on the top right, I will see like the impulse response function of the system from a point target in the scene, for example, a sync function. The width of the sync function depends on the bandwidth. The height of the sync function depends on the length of the pulse. And this is after pulse compression. If I have an extended scattering scenarios, like a complex electromagnetic scenarios with possibly an infinite amount of infinitesimal scatterers, I see the coherent superposition of all the impulse response functions summed up. And actually, what I see is the scene is limited, like 100 meters in case of automotive radars. I see all the signal after pulse compression in the first 100 meters, and then everything else is zero. And for the cross correlation is all zero. But is it really necessary that everything should be zero? The answer is not. It's not necessary. It is necessary that the cross correlation is zero only for those delays that are allowed by the targets in the scene. for all the delays that are more than the scene size, is not required actually the orthogonality. So the cross correlation can be even non-zero. And in there, I can inject information. How much? Well, as a rule of thumb, imagine to have a 50 microseconds signal. If you have a pair of glasses that can see this signal in space, this is 7.5 kilometer in length. And my scene is 100 meter. And all the other 7.4 kilometer are wasted space. That is there, and you can inject information there. How? Well, we developed a very simple algebraic, let's say, algorithm. It's a sort of double pre-coding, and each waveform, this is vector notation, each waveform is computed as this Cn and n beta n, where the only characteristics is that Cn are a set of matrices that allows orthogonality communication-wise. They are so-called keys, and these keys are matrices that are just orthonormal, so they allow to encode information inside the waveform and decode information from the waveform. So they're called keys because they are shared between transmitter and receiver. Obviously, for communication, transmitter and receiver are not co-located. So they just share this key, and they can encode and decode information from there. For what concern instead imaging or sensing, orthogonality is achieved thanks to this matrix N, and this matrix N basically is computed as represent the generator of the null spaces of the cross-correlation operators. Basically, we say, okay, we generate the first signal, and then for the second signal, we want it to be constructed in this way, but we search for that n, that null space descriptor n, that allows for the second signal to be orthogonal with respect to the first one. And then we switch to the third one. It's like an iterative approach. We start from the first, then the second, that we want it to be orthogonal with respect to the first, and then the third one, that we want to be orthogonal with respect to the first one and the second one, and so on and so forth. And we construct a set of signals. They can carry a huge amount of information. They are not TDM, so orthogonality is not achieved in time, is not FDM, because orthogonality is not achieved in the frequency domain, it's achieved in code. And they are orthogonal both communication-wise and sensing-wise and imaging-wise. And we can, in this way, encode information inside. We transmit all the waveforms. We record all the waveforms, the echoes, to the same Radcom devices that transmit the waveform, and we generate a radio image. But at the same time, somewhere else, another device, possibly even a CISO device with a single antenna, records all this waveform and is able to decode information inside them. And this was waveform design. This can be done in automotive, but also in with whatever platform. The second strand of research, actually Professor Spagnolini talked about this topic this morning, is cooperative, coherent, and multistatic imaging and phase synchronization in networked sensing. So imagine that you have a scenario in which there are several entities, several vehicles, that are equipped with a low-end sensor, capable of very low resolution imaging. So they can create very images that are really bad, actually. So because they needs to be cheap, and later on I will tell you in the next slide how cheap. And all these vehicles, however, are willing to cooperate. They can cooperate, they can share information, and low-end sensor can behave, if they cooperate in a meaningful way, in a proper way, they can behave like a very, very expensive automotive radar. So cooperation is activated by a V2V communication upon request of one of the user. One of the user requests, okay, I want to generate an image over there because I think there is a potential target there. I need higher resolution. And they all transmit on different bandwidths, so there is no interference. And they jointly process all these images to generate a very high resolution of the scene. And why is this useful? Because, again, each vehicle must be equipped with a low-end radar. So last year I was I was in San Antonio in Texas, and I talked during the gala dinner of a conference, RadarConf. I talked with a Bosch engineer. Bosch is like leader in producing automotive radars, and this guy placed in my hand one of their radars. It's like a 2x4 MIMO radar, and he said every car has like 6-7 of these. Can you guess how much they cost? And I said, well, I have no idea actually. And he said, okay, we sell millions of these, and they cost $25 each. If they cost like 30, no automakers are gonna buy them from us because they are too expensive, because they buy hundreds of thousands of these. I mean, high-end cars, they have 6, 7, 8 of these radars. And so they needs to be low-end radar. Low-end radar means low performances. It's not like an Harbe chipset, very high-end chipset with like 48 by 48 channels, like 2,300 virtual channels. It's very expensive for very high-end vehicles, and this must be cheap. However, N cheap sensors, if they cooperate, they can behave like a very expensive one. How? Well, again, they transmit, let's say, on different frequency bands, so they do not like overlap in the spectrum. And the tricky part here is, as always, as all the collaboration is like to be synchronized. It's also true in humans, but it's also true in radars. It's like trying to synchronize between everyone. And this is a 3-step procedure. We like estimate the frequency offset between transmitting and receiving. So we accurately recover all the transmitted frequencies. There is a coarse estimation and synchronization using just simple co-registration between images. The monostatic images are our sort of ground truth because they do not have synchronization error, because monostatic images, they are generated using like a single oscillator on a single device. Instead, what is problematic are all the bistatic, that they have synchronization errors. And so we try to take the bistatic one and match with the monostatic one, and from the shifts and the co-registration shifts between the images, we can extract the parameter of interest, so like the time shift, the frequency shifts, and so on, between the clocks. And then there is a fine estimation and synchronization using a PS-based phase calibration, PS, permanent scatterers, like prominent targets in the scene. And we do a very fine phase synchronization between different clocks. And as you can see, this is like a single vehicle, very poor resolution. This is the B-sync impulse response function. You can see just basically one target, and if you instead let everyone collaborate, you have like 2 targets appear, and we have also a pretty nice image that Professor Spagnolini already showed you this morning. And when we used some automotive real data, and we basically degraded voluntarily for the experiment, like the performances and of these instruments, and we have like the 2 monostatic, so 2 vehicles, they both generate radio images of the environment, and then the bistatic one, and by themselves, the resolution is pretty poor. You cannot see basically the targets. But if you let everyone collaborate in the proper way, the 2 feet of my colleague appear at a distance of 40 centimeters, which match the ground truth, which is the video of the GoPro on the top of the vehicle. So this is coherent fusion between images that require very fine phase synchronization, but it is achievable, and this was a JSAC publication already published. Another topic, let's step up a notch. So UAV-based synthetic aperture radar. My main research interest is about synthetic aperture radars and using OFDM waveforms. So let's suppose we have a UAV. This time we started actually from a possible concepts of like real application that can be really useful. So if there is, let's suppose in a remote area, like a mountain area, there is an avalanche, usually there is no coverage, cellular coverage. And what I want is like a UAV that goes over the region with the avalanche and scan the scene. It provides like a link of communication for the search and rescue team on ground, but also scans the image, and maybe you can see even underground what an optical system is not able to do, like see under the snow and possibly detect a target under the snow. And first of all, we developed a simulator. So these are the simulator is a flying base station that transmits standard OFDM waveform. By standard, I mean sub-carrier spacing is respected by the standard, the power is respected, the number of antennas, there is the noise factor, the typical noise factor of the receiver. Like, it's a flying base station with all the parameters of the standards, the most modern standards. And we modeled the snow using the literature, the power loss inside the snow, the electromagnetic wave, and so on. And we tried to see what is the depth at which we can see a 1 meter squared radar cross-section target under the snow, under like medium dry condition of the snow. And we can see the target pretty much under, let's say, 1.5, even 2 meters of snow, if it's particularly dry. And this is a possible application. And then we tried with real data. And these are two boys, Tom and Jerry. Tom and Jerry are our two UAVs. Tom is a little bit bigger, but the software is a little bit more stupid. And Jerry is smaller, but clever. And that's why Tom and Jerry. And we keep the two UAVs with these radars, and we generate radio images of the environment. On the right, the classical optical image. On the left, instead, we have what I called a radio image of the environment. This is an image, a radio image acquired using this radar, and then focused using a time domain back projection. And you can see something that you cannot see from the optical image. You see this is a little forest, and under the forest there is a fence. And since the electromagnetic wave penetrates through clouds, through smoke, through forests, rubbles, and so on, you can see like below the canopy, and you can see the railway. You can do change detection if you fly multiple times. And so this is the kind of product that we are able to achieve through imaging of the scene. Last, but not least, high altitude platform in the last 1 minute that I have. So high altitude platform station for the simultaneous networking, offloading, and extended scene imaging. Basically, we have like these very high altitude airships. They can fly, they are almost still, and the fact that they are almost still is good for both communication and imaging. The almost is the key. Almost still means that they are moving slowly, and the fact that they're moving is fine because we can do synthetic aperture. We can keep transmitting and receiving pulses, and then we focus them coherently to form the radio images of before. And they're almost still, meaning that they are like over a city, and they can offload the traffic from base station on ground. And this is like an interspoke and inter-university collaboration. We collaborated with Politecnico di Torino, and we developed, like we tried to assess the performances, both communication-wise and sensing-wise, of these scenarios. And we can see that we can form images for swaths of like scenes of kilometers in size. So the image that you saw before are just a few hundred meters, but we can form the same images for kilometers in size using hubs flying in different altitudes, and we can offload traffic and save energy up to 20-30% for what concerns the communication. So we can help in some specific scenarios, like the base station on ground, to like consume less energy. And I think this is my time that finished. No? So, but yes. Focus procedure to focus.
Thank you. Okay, perfect. So next is thank you again, Marco. So Egidio, okay, Egidio Ragonese is from Università di Catania.
Good afternoon to everybody. So this is the outline of my talk. This talk is from top to the bottom because I'm an electronic engineer. So there is, first of all, an introduction because most of you don't know me. And then some issues about radar for sensing, challenges and opportunities. And I want to give you an idea of what is the meaning of circuit design, so the trade-off about application design and circuit design. And finally, in my talk, I will show you a design example of a simple block, just to give you an idea of what is the meaning of, for an electronic engineer, for a millimeter electronic engineer, to do circuits that are for the application. So let's, and then there is some biography of this talk for the reader. So I grew up in Catania scientifically. I worked at the university for some years. Then I moved to industry in research and development in ST. And then I returned home here as associate professor. So my expertise in design of silicon integrated transceivers for communications and for radars. And since 2008, I was the first designers that tried to integrate fully integrated chips for 24 gigahertz applications. So it was a very important achievement in this field. Then I moved to higher frequency, 77 gigahertz, in BiCMOS and CMOS technology. So which is my role here? Why I am in ESA-Cage? I am in ESA-Cage to explore novel, effective, and especially practical solution for integrated circuits to be used in a millimeter wave transceiver for communications or radar. So just to don't forget that the bottom is at the bottom, there are everything is circuits at the bottom. Do you know radar better than me? So just to say that there is a metric that is the number of papers published when you search in IEEE Explore, searching radar and BiCMOS or CMOS, and you get that there is an increment of more than 20 times. This means that radar is not a new technology, but integrated radar, that means radar made up of integrated circuits, is about new, is quite new. This means that only when technologies, integrated technologies, became able to sustain these applications are now in our daily life. So the previous colleagues said that Bosch said that the cost of the radar should be very cheap because a lot of sensor must be used in a car, but this is a target, this is an objective that could be achieved only by using integrated technology, silicon integrated technology. So this is the point. So every solution should be integrated in silicon if we want that the technology, our architecture, your algorithm, and so on, can be effective in life in our life. So there are a lot of applications in which radar, starting from the driving application. The driving application, from my point of view, was automotive radar. When radar moved into the car as for detecting targets at short range, at 24 gigahertz, and then at long range at 77 gigahertz, it means that radar became a technology that is near us. And from this point, there is a lot of other applications that is derived from radar circuits. So from gesture recognition for human-to-machine interaction, sign language translation. We tried with some of colleagues of my department to use radars from Infineon to recognize signs for deaf people. Gesture recognition also for detection of movement. Google Soli project is something that is a reality just now. And there is also radar for driver monitoring in the car cockpit, so to avoid the sleeping of the driver, or to monitoring the vital sign of a patient in a hospital without any physical sensor on the patient, or for imaging sensor for diagnostic or for security. So a lot of application, but the main common factor is radar with integrated circuits. So a lot of applications and a lot of bands, from the lower bands, K-band, that was used at the beginning for a limited time or period since the technology was not mature to support higher frequency operation. So 24 gigahertz sensors are the whole generation short-range automotive radar, up to V-band, W-band, D-band, and higher bands. So what is the meaning of higher and higher frequencies? It means that when you move from low frequency to high frequency, you need expensive technology, and so the cost is higher, but also the reliability is lower. So take care that when we want to use higher frequency, this is not neutral. We have to build other system, other circuit with other problems in other technologies. So these slides is something that I imagine just to put together a lot of issues that typically are considered not together. Because we see the technology people look at the technology, develop the technology for circuit integration. There are people that look for application and give us the specification just for radars, resolution, range, angular resolution, accuracy, and so on. The brand, there is someone that says we can give you this band for this application, but at the end there is the design. And the design means that you start from algorithm, you start from modulation, system architecture, going from the top to the bottom up for, we want to design circuits, we have to design package, we have to design the antennas, we have to design the application board. We should be able to test these sensors. And if we think also to the specific IC design, typically electronic circuits for some people means something that is already done. It's not so. It's so for standard application. When you want to address high frequency circuits in very expensive and very complex technology, a lot of issues must be considered. And the work of the IC designer is not very simple, because we have to manage technology. The receiver should have a good sensitivity, a good linearity. The transmitter should be able to transmit high power, to have the good range. You have problem of bandwidth for the resolution, power consumption, because you know this sensor must consume very low power for energy efficiency. So a lot of challenges that are upon the IC design. So this is an introduction about the environment, since my field is a little bit far from you, and so just to introduce more in some details, which is our work. So now, I hope not to annoy you, just to give you an insight about a block. And I choose an oscillator, a voltage-controlled oscillator that is a key block in every transceiver, and its performance is crucial for the signal spectral purity, then the frequency span, and so on. So when you design a VCO at higher frequency, design is very involved, it is very complex, because the parasitics, the inductive capacitive parasitics in the resonant tank degrades the performance of the tuning range, and also the quality factor, the variable capacitor that are used for changing the frequency is another problem. So typically, when you want to design an oscillator for high frequency application, you design the oscillator at lower frequency and then multiply the frequency up to your real carrier, actual carrier. There is another problem. When you want to achieve the specification in terms of phase noise or spectral purity of the oscillator, typically this specification is very difficult to achieve. So a typical technique to achieve this target is to couple different oscillators in phase. When you have n oscillators that are in phase, the phase noise decreases with this formula, typically, theoretically, 3 dB every time you double the number of cores. Okay? So if you use 2 oscillators that are in phase, the phase noise decrease by 3 dB, 4 by 6 dB, and so on. So this is theoretically, because the real situation is a little bit different, because when you want to do this, you have to take into account that the power consumption increase your silicon area. So the oscillator is larger in your chip, and every circuit designer has very strict constraint in terms of silicon area. Silicon area means cost, and also power consumption. And also, when you increase this number, n, you couple 4, 6, 8 cores, the complexity of the coupling network, the network that couples this oscillator and makes them oscillate at the same frequency in phase, is too much complex, and this can degrade the performance. So typically 4 is the magic number. So the quad-core solutions are the trade-off for this type of architectures. So, and typically in literature we have 3 approaches. The classical approach proposed by Professor Svelto, University of Pavia, multi-port inductor proposed by Professor Isakov, and staked inductors by Professor Darami. And just to give you some idea, the first approach is the simple one. You have 4 cores that are here orthogonally distributed, and a centroid structure and a coupling network that is resistive to couple the oscillators. It's low complexity, the design is simple because each oscillator can be designed individually and is not coupled with the others, but the area is very high because you have a lot of area used for the 4 cores. So there is one tentative to change this architecture is this multi-port inductor in which the cores are connected by microstrips. So this microstrips is like a big inductor that that couple the 4 cores. So again, the silicon area is very high, but the quality factor is high, so the phase noise performance is better. The third structure uses the approach of staked inductors. Save area, but the performance are poor. What we propose inside is a cage. Inside this cage, we propose two solutions. The first one was recently published in Electronics, is on the left, and the second is published first, it was patented in USA, and then published in IEEE Access, and they are based on different approach. The first is a modification of the staked structure based on this inductive structure that is named, the name is interstaked. And the second is based on this structure that is staked to port inductor. A staked to port inductor is something that uses a mixed effect between the staked transformer and the multiport, and this was patented. So we at least integrated the circuits. This is, I cannot show you the photo, but I can show you the layout with some detailed structure. And it's a 20 GHz quad-core VCO based on this patent. And it was integrated in a 28 nanometer fully depleted silicon on insulator CMOS technology by ST Microelectronics. And it is under fabrication, and we expect good results and the demonstration that this idea could solve some of the problems of millimeter wave oscillators. And I conclude my talk. This is the biography related to this talk. Thank you.
Thank you. Thank you.
Okay, we are starting this session with an invited presentation, and the presentation is entitled Unreached Technology Outlook and Research Activities for Beyond 5G and 6G. And the presenter is Jonathan Borrell, that has over 30 years experience in the area of advanced RF and communication systems. After graduating from the Southampton University in the UK in electronic engineering, Jonathan worked for the UK Ministry of Defence developing advanced millimeter wave communication system. In 2001 he moved to Anritsu, and thereafter performing business development and management roles for the EMEA region. He was appointed as CTO for the test and measurement business. Jonathan is a full member of the Institute of Engineering and Technology, the IET, and chartered engineer. Jonathan, thank you.
Okay, thank you. So, yeah, I'm going to take a few minutes now to give you industry perspective from Anritsu. So, what are we doing in the area of beyond 5G, 6G, talk about our outlook, and then talk about some of our research topics, hopefully touching on a number of research topics that I've heard today. But just very quickly, Anritsu. So, some of you may know who Anritsu are, but just for your notice. So Anritsu from 1895, so coming for now 130 years in this industry, in the telecommunications industry. So starting from 1895. And actually it's a little bit interesting. You talked about recreating the work of Marconi. So actually the history from 1895 is our founder in 1890 went to the US, saw the activity of Marconi, came back to Japan in 1895, founded the company, which is now Anritsu. So we have some close remote link actually to that activity. But we've been in this business since 1895 in the telecoms industry. So what's 5G and beyond going to bring us? Obviously one of the key questions, use cases, why do we go beyond 5G? What's 6G? So honestly speaking, today, what is 5G? It's faster downloads. It's still cats and dogs videos, people streaming on YouTube. This is the reality that we have today, I'm sorry to say. What we're doing is more reliable connection, better coverage as the old 2G, 3G networks are switched off. But what's coming next then, of course, is these use cases that we've talked about today. So wireless connectivity with precision time, precision location services we've talked about. ultra-high reliability services. So both reliability from a radio link, but maybe also reliability from a transport network link. The low latency services and the ubiquitous coverage. So these are the things that we try to achieve now beyond 5G, 6G. And the question of why don't we do it in 5G, because these services are available, and actually what technical enhancements are needed to make it effective in 6G. So from Anritsu's point of view, we see three fundamental technology pillars behind all of this. Everything that we're doing, everything that we're looking at in 6G is based on these three pillars. And I think it kind of aligns to what I've heard and what I've seen on the posters. So AI/ML, of course. You know, you can't come to any conference today without talking about this topic. It is initially applied into the 5G network, but it's a real retrofit. We're trying to bolt AI on the side of a network that never had it. In 6G, we want to design it native, so fundamentally design it into the network and make it an end-to-end function. Virtualization, again, has been applied. The 5G core network is a virtualized core. We start to see things happening, for example, with O-RAN on virtualizing the RAN network. But 6G will be designed to be a fully virtualized complete network. And the third part then that goes with the virtualization is the distributed computing. So moving away from dedicated boxes, using servers, using commercial technology, and distributing the whole network computing function from the device to the base station, to the edge, to the central cloud, and smart and intelligent on how we distribute that compute function. So a lot of work here looking at the offload of function. As we bring AI in, we need to think about where do I do this AI? Where and when could I offload a processing task to another compute resource? Kind of interesting because people talk about self-driving cars, smart cars, and how AI is going to do all this for me. But if I've got an electric vehicle, you know, as soon as I switch on the AI, boom, well, I've run out of battery. Okay, that doesn't work. So, you know, you can't do all that processing on the vehicle because it will kill the battery. Can I offload a compute task to the network opportunistically when I'm in a good coverage scenario? This is a key question to look at. So, how do we envisage all of that? Well, really quite simple. We have our legacy services, our legacy networks, 2G, 3G, 4G, built around voice service and built around conventional network architecture. In 5G, we made our first moves. On the right-hand side, you see software-defined networking, network function virtualization. The core network was virtualized, and the core network does have AI function in it, even today. But the left-hand side is all conventional. So now, as we move towards 6G, we first of all go fully virtualized, one continuous cloud deployment of the network function, but also we distribute the AI, and in fact, not only core and RAN, but in the cell site and even in the device itself. So fully distributed AI across the network. What we have today is just individual pockets of AI. And then O-RAN is the current trend to move towards the cloud RAN, but maybe 3GPP and 6G will do something more designed in. And let's see whether O-RAN continues. So how does that all bolt together as a network? So I can think now that I have here, I have a central cloud compute facility, I have some edge cloud location, and I have some rural sites, some urban sites that I want to cover. And actually, I can put together a network. Oops. So I can build a first network here using some core network and some central cloud deployment. Use an edge cloud, maybe, to put some local content. Put a DUCU, or maybe actually then put a remote DUCU to a rural site here. Secondly, I can think of an urban site. I can put a second deployment using that same cloud infrastructure. So here the data center, the cloud infrastructure is the same. And in fact, this can represent two operators. So I could have two different networks, two different network operators very much sharing the same data infrastructure, and this is really the trend that we're seeing in the industry. And then, of course, I can have some dense urban site deployment, again, using that same data center. Because remember, the central cloud location, we often think that the central cloud is 2,000 kilometers away. But if I get in my car and I drive 2,000 kilometers and I park in the parking lot of the central cloud is 100 meters away from me. So we still have these deployments to think about. So really what we look at then is putting the different front hall, the mid hall, and the back hall, and all of this data center interconnect, the DCI, is the really important part. How do I transport data between those entities? And particularly then we'll talk later about the all-photonic network. So our trend is to use all optics in this interconnect system. So this is the overall view that we have then of the research topics that we see in the industry today for this beyond 5G, 6G. And again, broken down as an end-to-end architecture. So on core network side, the onboard optics, the silicon photonics, the all-photonic network, NTN and heterogeneous network, and then the distributed architecture we talked about. Baseband, of course, coding and error correction schemes. A little bit early for that work, I think, at the moment. Still some heavy discussion. Should we stay with OFDM? Should we move to a new waveform? In the radio side, a lot of activity, and perhaps something we've talked about a lot today. So putting AI/ML, for example, for spectrum sharing and for scheduling algorithms. Terahertz device technology, terahertz device related waveforms. Do we go back to a single carrier waveform for very wide bandwidths at sub-terahertz? Why would we stay with OFDM at those high bandwidths? And then integrated sensing communication. From an Anritsu point of view, one of the other interesting areas we'll talk about is actually the propagation channel. So the channel modeling for that propagation channel, the ISAC modeling for that propagation channel, and then the RIS modeling and the RIS evaluation for that propagation channel. So we certainly see a lot of activity in that channel, and I think today I've seen corresponding a lot of discussion from the research programs in that area. And finally, I just want to highlight energy efficiency. It is a really big topic for the industry. Everywhere we go now in telecoms, energy efficiency is heavily discussed. How can we improve it? And not only on the network side, but also on the device side. So you may not be aware, but EU's just introduced a new regulation. From mid of 2025, if you go to the store and buy a new smartphone, it will have an energy label on it. Like when you buy a refrigerator or an oven today, it has an energy label. EU has regulated a smartphone and a tablet will also have an energy label on it from mid of next year. So it's really serious across the whole industry. And just putting more data and more processing, more features on the handset actually isn't the way forward for us. So finally then, looking at the industry view, timescales of 6G. So where we are today is still in this ITU vision, so really making a vision of 6G. The technology demonstrators and the use case demonstrators, as we've talked about today. Next stage, however, is actually moving into the standards process. So 3GPP will be starting their standards process from March 2025, so less than 12 months' time. First technology workshops looking at 6G. And then by 2029, we should have our first standards. So really we start to prepare ourselves now for this transition from vision and technology use cases into early prototypes and pre-standards activity in the industry. And then first deployments, 2028, 2029, and mass deployments beyond 2030, would say, as a time frame. So very quickly, on the topic of frequencies, what becomes very clear now is that for 6G, the big discussion point is FR3, 7 to 24 gigahertz, particularly 7 to 15 gigahertz is the big topic. D-band has some interest. It is a technology under study for INT 2030, but no clear way forward yet. And then sub-terahertz H-band, actually not on the agenda for IMT 2030. So I would say that currently it seems not a candidate for 6G, but still very much a candidate for wireless communication. So other wireless application, particularly, for example, inside a data center link, where a mesh network inside a data center could be effective. Inter-satellite links in space, where high bandwidth communication is needed. Even then, D-band going on from a ground station to the air as a high capacity link. So there are many wireless communication applications for sub-terahertz, but IMT 2030 is not currently one of those, and the big focus would be onto the FR3 band. So that was a very quick summary of the industry. Now to talk about what Anritsu is doing in this area of 5G, beyond 5G, 6G. So our 6G research program breaks down roughly like this, corresponding to the key topic areas. And I will attempt in 10 minutes to run you through just a little taster of each of these. So up at the sub-terahertz band, we have some 300 gigahertz test and measurement activity. So our challenge is always to say, yeah, I love your presentations today. I love all your designs. How are you going to measure it? How are you actually going to measure it? And that's we have as a test and measurement company. How will you measure that? So we're looking at spectrum analyzer, phase measurement, VNA measurement type technologies. We have then some novel channel sounding techniques and novel ISAC measurement based on some patented technology we have from Anritsu I'll mention. We're very much into the AI model, particularly life cycle management as we start to deploy AI. That's one of the key topics. Also then the distributed AI that we talked about in previous session. So actually splitting an AI function between a handset and a network becomes very challenging for us because the two algorithms actually have to interoperate together. So whatever handset, whatever network you have, they need to work somehow. And then also then some field test solutions which are actually based around data center, investigation into the green future network, energy efficiency, and then some joint proof of concepts we're doing on the all-photonic network. So sub-terahertz. The first topic we looked at on Anritsu was 300 gigahertz spectrum analyzer. How are you going to measure the output spectrum? You say, oh, normally it's easy. I get a down converter. Get a down converter, mix it down, sweep the yellow, I can do my measurements. Yes, very nice to use a down converter, but the mixer in your down converter has so many issues. The intermodulation products, the image products, that actually when you look at the output screen, you don't, well, is that the device or is that my test equipment? Always with the spectrum analyzer, we have a pre-selector filter at the front end before the mixer to remove all of those issues. So the pre-select filter is the key that makes it a spectrum analyzer and not just a down converter. So for us, we have developed, and you can see the picture on here, 300 gigahertz pre-select filter. That means tunable, switchable 300 gigahertz filters with very, very low loss. And that's been our development. And we have a concept and we have a demonstrator here. This front end, so tuning between 275 and 315 gigahertz and sweeping and switching filter bank across here, very, very low loss. Second challenge we had was on phase compensation system. So if you're building a 300 gigahertz wideband system, let's say 10 gigahertz bandwidth, and you actually want to measure the phase flatness of your transmitter, okay, but my test equipment's got like 20 degrees phase error. How am I going to measure it? So how do we make a very phase stable sampling system? So it's a little bit difficult to see here, but basically what we're doing to get 10 gigahertz of flatness, phase flatness, we switch from the microwave domain to the optical domain. Because for a laser, 10 gigahertz of good phase flatness is almost insignificant. So our technique here is to free space couple the 300 gigahertz signal into a lithium niobate crystal, use a laser to then illuminate the crystal to measure the intermod product between the microwave and the laser, and therefore giving the laser measurement, giving us the very good phase flatness. So we've built this system, we've verified it, we've presented some results, so we're getting better than 5 degrees phase flatness over 10 gigahertz of bandwidth with this system. Third then is our broadband's VNA. So here we have our VNA system where we actually move the VNA measurement port right to the front of the head. So it's not down converting to the VNA, but we bring the VNA right to the front. So this then gives us very, very high accuracy and single sweep measurement. So 70 kilohertz to 220 gigahertz, single sweep, no changing of converters, no changing of anything. It's all done by the front-end module of the VNA. Second area is an area on channel sounding. So we've been working closely with University of Aalborg in Denmark, using our patented VNA, so remote VNA here, where we actually split the two VNA portions between one side and another, and we have just fiber optic cable to link them together. Key point is that the VNA itself is at the measurement port. There is no cabling from the VNA to the measurement point. It's not up converting. It's moving the VNA itself. And we're able here to do actually simultaneous FR1, FR2, FR3 measurements, same time, same place, same antenna. And this work was in fact submitted to 3GPP RAN 1 as the only data in the world that shows us FR1, FR2, FR3 simultaneously. Some examples of that. So here is looking at a outdoor line of sight, non-line of sight scenario. You can see that line of sight, everything is good at low, mid, high frequency. Non-line of sight, at low frequency, I've got good reflection environment. MIMO works nicely. But it seems like the FR3 environment is much like FR2. Very poor reflection for a non-line of sight environment. And this was done in a very, very large measurement campaign we did. Equally then, indoor measurement. So this is doing the same thing in a smart factory. What's nice here, of course, is the VNA is just this little box here. So very conveniently, we can move our measurement method when you want to do channel sounding and you want to do mapping of a smart factory. Previously, I think you'd have a student and a trolley and move them around and make measurements. Now, of course, the whole system is so compact, we put on a little robot, and the robot drives around and does all of our measurement campaign for us. So that was used to map an entire 5G smart factory. Finally then, we've also used the same VNA technology for ISAC. Remember that a VNA, we get the S11 reflection and the S21 transmission, phase and amplitude. And so we can use that system here to recreate, here's inside a room, and we're measuring now delay, therefore distance, and angle of arrival, and mapping out the reflecting surfaces in the room. This can then be ray traced across into locations of devices, of reflectors, and of course, as any transient comes into the room, we will pick it up on here. So we've been using this as a way of doing calibration measurements on sensing inside a room. And you see some example of some measurements here. Next topic then, very quickly, AI. So everybody knows AI. The fun fact of the day, time to reach 1 million users. So Netflix took 3.5 years to get 1 million subscribers. You see here, Facebook took 10 months to get 1 million subscribers. ChatGPT took 5 days to get 1 million subscribers. I mean, it's just phenomenal how quickly it's taken on. But the question as it comes into your daily life, if we think about a car driving down the street, if we think about a mobile network being managed, how can I trust AI? It's the key question of trust. Are you going to be trusting AI with your life in a smart car? Who knows? So, it's a fundamental issue. Is it accurate? Is it true? Is it biased? And from test and measurement, this is our contribution because we put together the approval, the certification schemes. How you generate trust is by saying it's been certified, it's been approved. So how do I put together an approval scheme, a certification scheme that proves an AI system is doing what it should do? So the example I would quickly show here, this is actually looking at that distributed AI topic that was raised in the earlier session. So here, inside a mobile network, we actually have half of the inference in the DUT, which is the handset. The other half of the inference is actually inside the network, and they're doing a joint inference. In this case, it's actually the CSIRS reporting. So when the UE measures CSIRS, rather than send a whole CSIRS report, it's actually done as a semantic report by using a compression encoder-decoder to achieve this. But then we have to get into all the lifecycle management, the data set description, the KPIs, etc. So very quickly, we build together an architecture that shows the various factors. So how do I control it? How do I do the simulation? How do I do the coupling and the generation of scenarios? And what we've done is very simply embed that into a network test system. So with this system here, basically, I go out in the field, I capture data. This is ground truth data, real network data. I can then convert that into a digital twin scenario. This then comes into the lab where I now actually do my data science on that data set. I create the bias that I want. I create a certain bias, or I remove another bias. But I engineered the correct type of data that I want to use, run that data, and then through that system here, I can then generate all of my training data, my training methodology, and then do my validation system. So this is a whole system for doing it based around our network simulation technology. Finally then, the other area of activity we have is in IOWN, Innovative Optical Wireless Network. So this is a technology where we're trying to integrate wireless and optical seamlessly, and particularly this all-photonic network. So one of the areas of research is full-stack communication. So rather controversially, replace TCP/IP. So everything we do, we have 2G, 3G, 4G, 5G, 6G, blah, 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 blah. It's all based on IP. It's all based on a 50-year-old protocol. Is it maybe time to think about, perhaps, updating or changing or doing something? So one of the thought areas is, how do we move beyond IP-based communication? What should that look like? How should that operate? Also then looking at this all-photonic network. So the example here is, I have a data center server with a memory talking to a CPU. Today's architecture, of course, I go through some copper backplane, I go through another backplane, I go through another converter, I go through some optical interconnect, I go through some long interconnect, I come back. I have so many layers of interconnect to transition through. IOWN is basically taking me all optical from the processor element, from the CPU, GPU processor, optically off the chip, optically across the backplane, optically on the interconnect, and end-to-end to the other end. And then this brings me to this data-centric future. So how do we move to a data-centric architecture? So the network architecture is designed by the function, not by the task. So it's not about moving data, it's about delivering function. And this brings in, how do we move beyond the traditional IP network, rather than being IP-centric, move to this data-centric, function-centric network. And just quickly as example then, Anritsu's active within this area. So we are working very heavily with some partners on co-packaged optics, a CPO measurement system here with Kyocera. The optical path measurement, which I think came in the previous presentation on the optical side. So how do I do the GSNR, which is actually the end-to-end signal-to-noise ratio? Because my problem here with this optical network is I can't actually probe inside the network to measure SNR. So I need a new SNR measurement system, And this is the GSNR to replace the bit error rate measurements. And then also working very much on the latency side. So we have some very innovative technology of high accuracy latency end-to-end networks. And this is microsecond latency projects. So we're collaborating, for example, with NTT in this area, doing the end-to-end latency measurements. So finally then, just about on time. So what I talked about, the timelines for 6G are now being prepared by 3GPP. We have been through this phase of fundamental technology. The use cases are under discussion now to show how we can enhance capabilities, and that sustainability and energy efficiency becomes a key topic. We talked about the frequency plan. So upper mid-band is the high priority. The technology studies are underway for the 100 gigahertz, let's say 100 to 200 gigahertz band. But there are no clear plans yet for 300 gigahertz utilization for IMT. But certainly there's still research for the wireless, general wireless communication. And then finally talked about Anritsu's participation. So we're doing the channel sounding and ISAC methods. We're doing FR3 and air interface measurements. We're doing some AI testing, test tools for AI, and also then the IOWN optical network and datacomms testing. And finally then just some of the industry forums, so some of the global industry forums which are very active within these areas that Anritsu participates in. So hopefully not too much over time. Thank you, and any questions, please?
So I asked the panelists to come to the floor here. So apart from Jonathan, Paolo Marini from Keysight, and Daniele Munaretto, Roberto Candela from Prismian, okay, and Federica Bruschetta. Okay, so please. So we have a very hard job now. It's 5:45. We are here since 2 p.m. without stopping.
Yes.
Okay.
And we still have one.
And you are not paying for that. And you are not paying for that. So.
Now we show we are hard workers.
Yeah. It's a demonstration of power. Okay. So I would like, first of all, to thank you all for being here and to take part of this panel. And apart from Jonathan, that has been just speaking, and we'll let him to breathe a bit, I would like the panelists to introduce themselves and talk about their company and their role in the company. First of all. And please, Federica, if you want.
So, good afternoon, everyone. So I'm Federica Bruschetta from CI Microelettronica. CI Microelettronica is a company which design, develop, and deliver radio microwave links and microwave radio equipments, as well as the software to manage them, that is the network manager system or an SDN controller. And CI Microelettronica also provides wireless network solution. So at CI, I am in charge of, I am a software program manager, and I'm experienced in networking and artificial intelligence. And in restarts, CI Microelettronica is in charge of providing a proof of concept demonstrating the dynamic way to perform a network resources allocation through artificial intelligence techniques.
Okay. And please.
My name is Paolo Marini. I'm with Keysight Technologies, a global company that dates back to the HP area back in the 30s, one of the first startups in Silicon Valley. And Keysight Technology mission is to connect and secure the world. So it's a technology leader in test and measurement systems, covering a broader portfolio of the communication systems. My role within Keysight Technologies is a product manager for RAN and DORAN testing solution. Actually, in Milan, we have the most important part of the Edge-to-Core division, which is focused exactly on developing multi-terminal emulators for testing both radio access network implemented in aggregated and disaggregated ways. We have other testing solutions focused on massive MIMO, and as part of this, we are working on an emulator for cell-free massive MIMO networks.
Good afternoon. My name is Roberto Candela. I am the CEO of EOS. EOS is a company of Prysmian Group that is focused on deliver, design, and install monitoring system for cable application. As you probably know, Prysmian is the biggest cable maker in the world. We are an Italian company that is focused on produce copper cable for all the application, fiber optic cable for telecommunication, for different kind of application. My role in the company is to drive a division that is dedicated to develop electronics, to integrate the cable, to have more information about their behavior, and to understand if they are performing at the maximum speed, with the maximum capacity, with the, in terms of performances. In Restart, we are working on a project to extend in an unlimited way the possibility to measure with the optical sensing solutions, so DTS and DAS, temperature and noise around cable, to avoid, first of all, the overloading of the power cable, but also to understand, for example, in case of fault, where the fault is. And we are talking about cable system longer than 200, 300 kilometers. So the complexity is not
quite high. I do imagine. Then the last for Daniele.
So, good afternoon. I'm Daniele Monaretto from HP, former Atonet, acquired in September last year. And I'm head of research and innovation in the company. Our focus as former Atonet is on private mobile networks, where we are quite a pioneer. And our research focus is on the evolution of the network functionalities, with focus on the core network side, but not only, as we focus also on all the verticals and use cases related to the use of private mobile networks, of course. And that's it.
Okay, thank you. So the first question that I would like to pose to everybody, each one makes a different focus, but you are all companies, and the main target of a company is to sell products, okay? And therefore you produce something that you want to put on the market. And the market is plenty of innovation now, artificial intelligence, machine learning, that you may put in any part of your product lifetime, for instance, but also, for instance, virtualization, that is another big part of this. But when do you think that your products will effectively will implement those changes for products on the market? Or it's just a question of names and fashionable? Yes, please, Jonathan, if you want. Here it is.
This one. So yeah, it's a challenge on, you say, how we bring these technologies actually to commercial market, how we monetize those things. So we actually just started already with the AI topic. I mentioned network monitoring solutions. So for example, the network monitoring is now using at least machine learning, let me say. We've recently demonstrated some AI actually for signal analysis. So actually bring AI into this topic of, okay, I've got a complex RF spectrum. How do I understand and analyze all these different drones and what they're doing, for example? So yeah, it's just now starting. The next challenge, I think, is generative AI, because the big hype on Gen AI and how can you use it. So it's looking at what does Gen AI mean for users, our users, as test and measurement? You know, is it something about the user interface, about prompting, about scripting, about the way you interact with a piece of test equipment? I think you've all been frustrated of where in the menu do I do this? You know, and can Gen AI, as we saw some of these, you know, how can I think there was the presentation on the automation of the optical network. You know, same thing. How can I use Gen AI to ask a question to my test equipment? And it gives me an answer.
And above all, what is the trustability of that?
I was going to come to hallucination. Hallucination is the problem there.
Thank you. So, as a CI microelectronica in terms of artificial intelligence techniques, already deployed some application and services which adopt artificial intelligence techniques indeed. For instance, we address the classification problems, and unsupervised learning problems, while providing preventive maintenance, for sure, which is something very hot in the area of the telecommunication and backhauling as well, but also to classify the failures in the network, as we have the possibility to treat and manage a huge amount of data, as we gather performances, radio performances, as well as alarms and so on.
So life cycle management, let me say.
Yes, correct. So we have this huge amount of data, and we exploited them in order to provide intelligence services. So, but what we see next, the focus is, as I was mentioning before, is also about optimizing the network resources. Obviously, the focus in mobile backhauling networks, and that's another topic, other AI techniques where we do adopt, in this case, reinforcement learning techniques. So why automating, and why artificial intelligence while managing the network resources allocation, for instance? So if we take, for instance, a concrete case like the requirement of frequency reuse, which is more and more crucial as long as the network architectures evolve. So with a static, with a traditional network planning, the planning is done statically, by definition, and based on the worst case. So we need to make the process dynamic. And, but dynamic with artificial intelligence is a problem complex, very complex. It cannot be addressed, or better, addressing it with a traditional programming would require an extensive rule setting. So that's where we are.
Okay. What about Keysight?
In Keysight, we already work on artificial intelligence. If we look at the 5G networks in their disaggregated implementation in ORAN-based network, intelligence is already an open component. If we think about the RIC part of an ORAN network, it's an open implementation of the network intelligence. And what we already do since quite some time is to provide the ability to test the algorithms within the RIC, so the algorithm that implement the network intelligence focused on energy efficiency, focused on MIMO management, focused on coverage management, and these algorithms need to be trained. So training of algorithms is an important area for a tool vendor, where we have to provide standardized methodologies that leverage on open interfaces that are now one of the key pillars of new networks in order to train the intelligent algorithms that are part of the network. Then if we go down up to the physical layer in 3GPP, we see already some advancement on which we have some implementation of AI ML for the radio algorithms, and we are working already on implementing this kind of training sequences, training applications that are focused on testing the radio access network. In general, AI ML applications are pretty pervasive, and so as part of the test and measurement solutions that we provide, we always focus on implementing some intelligent part that enables a quick resolution or finding issues in a much faster way. Examples are finding a sequence of a protocol sequence where there are some errors, and so dig down to the error to save some time from the development. So as we can see, AI ML is pretty pervasive, both in the technology and also in the way the technology is developed and tested. The goal, of course, is to make it work better, smarter, and also to lower the time to market of the network implementers, of the network device vendors.
Okay, thank you. Yes, please.
Yes, in Prismian we sell artificial intelligence products at least since 10 years. Basically, we apply artificial intelligence in two main fields. The first is the noise recognition through the fiber optic application, so through the DAS application, to understand if a cable system is attacked by an anchor, by a fisherman, by a submarine, or by something else. So basically, we recognize pattern of noise to deliver to our customer the information that which kind of attack is suffering the cable. This is applied also in the land cable, so you can apply this technique also in land cable, and so basically you recognize digging from other human activity around the cable. For the TSOs, so the transmission operator, this information is very useful because you can understand if your cable is in a dangerous situation or not. The same happens for telecom application, so for communication application. And this is basically the same approach because at the end the sensor is the fiber, and we use the fiber and the signal acquired by the DAS to analyze this data. The second field where we apply artificial intelligence came from my previous life. I was former professor at University of Palermo for electrotechnical. And at the time I developed some algorithm to recognize partial discharge pattern for understand defects on high voltage cable system or high voltage accessories. And now we sell these products as a software that give to the user of high voltage network the information that a joint is going to be faulty or a cable is affected by a potential damage in a few months or a few weeks. So this is still products. Obviously, with the increased power of the electronics and the computational power, it's possible to be faster, more reliable, and cheaper in this kind of delivery.
Daniele.
Yep. So, AI clearly is here. I mean, we're not talking about something that is coming, but it's here, right? And it is already clear that it's key for industries to win, the competition. I mean, to win in the market. It is completely clear. This, and in the last Mobile World Congress in February in Barcelona, I mean, all companies, big vendors, operators, and so on, clearly stated that if you want to win in the market in the next years, you have to be the quickest in adopting AI and follow also the evolution, the quick evolution of AI. The colleague from Maurizio was talking about GenAI, but I mean the evolution is very rapid. So it's not that easy to follow and to be always, on track. So it's quite a challenge. Just saying, so I don't use the hat of the head of research and innovation. I now take the hat of a salesman. Okay, and if I look at 2 moves of my company, so the acquisition of Juniper, which is famous to be one of the first industry in the world introducing AI in the switches and all the networking components. And looking also publicly at the last quarter earnings of the company, where most of those earnings were coming from AI-based products, it is clear, I mean, in my view at least, that AI is fundamental for industries to win. That's clear. And it's important to really follow as close as possible the evolution of such algorithms and tools that can provide it to improve automation, improve many things that can help industries to evolve products and be always the first, so at the edge of the technology, in the market.
Thank you, Daniele. One question for the let's say instrument providers. You are basically a final node of a large network, and how will you think to benefit from the additional services that this network is growing and the additional bandwidth, the additional centralized capabilities that will form the basis for the 5G advanced and the 6G. So you as the final node of a large network. That's it. Whoever is, you can start if you want. You can take mine.
Yeah, so if I understand the question right, then it's about how, as an instrument vendor, we actually use the network as a part of, for example, a test solution. I think that's where I emphasized in my presentation about virtualization, that you start to virtualize the measurement function, that you have some, if you take a piece of test equipment, you can decompose it and basically disaggregated test equipment, if you like, that you can take the sensor function, take the data acquisition, take the processing, take the user interface, disaggregate, and once you have disaggregated, you can virtualize, you can distribute, and that's where the network comes in, that we then use the network to, for example, house some measurement function or some archiving on a remote cloud. You start to offer as a service. So you have for example, an RF test equipment, you have a piece of RF equipment, you have an RF sensor, you have an A to D converter, and the rest. The rest is virtualized, and it can be a spectrum analyzer, it can be a VNA, it can be a phase noise measurement, or whatever you need. And that allows us to then virtualize and offer as a service. So I think this is where network connectivity comes in. And of course, again, that's closely linked to the topic of AI, because once you can centralize all that data, you can then get a much better understanding of the data. You can maybe group data, you can offer more community-based type of measurements about community-based testing functions. So I think it's about disaggregating the test function and then deploying it using network infrastructure.
Yes, we as Keysight, we go into a similar direction. Let me provide you some examples. So currently, particularly in greenfield operators that started deploying disaggregated networks, they have a workflow where you have continuous design, deployment, integration, testing, and so as part of this, the continuous integration and testing is an important and key aspect, because the network is continuously upgraded, the new features are added, and so they need to be tested. As part of this, the testing solution run in the same network environment, so into a cloud network environment, and as are a part of testing automation tool chain. Normally, this type of testing solution are focused on end-to-end functionality, so generating traffic against a real network in a controlled environment where you can reproduce errors and validate new implementations, and also leveraging on digital twins where you collect data from the field and you replicate them in the lab in order to exploit issues and reproduce them in order to solve them in a controlled environment. So let me say that test solution is getting into the network as part of the network, as part of the continuous integration, continuous deployment, and continuous testing inside the network.
Just a small replica to both. This passage is now, to my opinion, very similar to what has happened a few years ago, in which the hardware, some parts of the instruments were changed by the firmware. And the users didn't trust, simply. Because what is hardware is metal, is rigid, is something that I trust. The firmware is something that is midway with software, so it's not really something that I can trust. So this passage from the real measurements to some virtualization is quite risky from the point of view of the user. Okay, it's a problem of trustability, but this is the user point of view, simply. Yes, if you want.
Could I just put a comment to that? I thought you say trust. Of course, trust is about the source. You know, where do I trust the source that it's coming from? And this is, you know, one of the challenges in the test and measurement industry is, of course, open source. That you can actually just buy an SDR radio and get a piece of open source code and you can do it all yourself. But as you said, do you trust that piece of open source code, or do you trust a professional grade test and measurement vendor? So yes, trust is very much the issue we see there. And open source is on the market, it's a reality we have to look at.
And regarding the continuous monitoring that you are doing in your company, which are the possibilities that are offered by a network that actually may also monitor physically? We have been looking at many advances from this point of view, from communication and sensing, in which you can simultaneously use let's say, a signal to identify and monitor even your
From this point of view, Prismian, it's a company that acts from two sides. Because from one side, we develop fiber that are more and more faster, more and more smaller, more and more. So we work as a cable maker, fiber maker. We work in increase and extend the performances of the metal, of the physical part. From the other side, we leverage on the fact that knowing very well the application where we provide this kind of cable, we are able to understand as much as possible what is possible to do with this kind of object. And at the end, we try to extend the concept of the continuous monitoring in object that until now has never been affected by this kind of things. Think about the typical situation is the cable market. When I enter in this market more or less 12 years ago, nobody take care of what is happening on a submarine cable. You know how much energy you push in, and not everybody knows how much energy came out. Now monitoring is mandatory. All the tender that you can find in the world for power connection between two medium voltage cabin or two countries are including monitoring system. So it's something that is growing more and more. In my opinion, depends from different kind of parallel effect, but it's a clear effect. And obviously, we as Prismian are in a position to work in different streams to increase from the one side the demand, and from one side the performances.
Okay, okay. Clearly, anyone may. Antonio, do you want? You are always so active that you cannot but.
I'm not an expert of technology, but maybe one question. You know, somehow we are witnessing. I mean, of course, you mentioned the big change of from hardware to software, which is a big change in technology. However, there are some other novelties that are coming in the technology, and maybe in your specific domains of expertise, what do you see can be the next big thing that can change a little bit the landscape? Because of course, honestly, except from this change in the virtualization, we didn't see very big changes in the last years, right? So is there anything on the view that can a little bit change, how we think, and we are seeing the technology in our sector is evolving? It's complicated, I guess, but...
So you are looking for a game changer.
Yes.
Okay.
If you want, I can start first. As said before, I believe that the pace that has AI now, we've never seen before. So I really believe this is something important to mention. And I think that we don't know where we go now with this. Probably next year we will say that, the world...
You don't think we are overestimating this?
No, we are underestimating it, for sure. No, because the pace is, the highest ever, and so for that reason, it's really difficult to foresee this. So I will put this as one big thing, And for sure, this will open many doors. And it's now opening doors because, automation as we conceived before completely changed now. So we were talking about real time here and there, failovering here and there, a robust thing like UR, LLC services, blah, blah, blah. But now it's happening because you have the tools, you have the computing, power and all the things that you need to really do it in real time. And having like networks, complex networks to adapt real time, be robust for any services that you can run. And in the next months and next years, we will have more and more demanding services on this. So I think we were underestimating this, and things will dramatically change soon.
I do agree.
So if I can comment on the same, so I do agree with with a colleague from Atonet. As I believe that automation is becoming more and more crucial, and this is somehow connected to the topic before, so the monitoring. So one technology that is coming and for which we are receiving a lot of requirements from customers, from mobile operators, is about network slicing. So network slicing is something that requires monitoring, continuous monitoring of the network parameters in order to grant a certain level of services, the service level agreement, basically. But it also requires automation to react, to take action automatically while the service is no more granted.
Yeah. Yes, please.
Yes, I perhaps had a comment that it's a really nice question. We can answer the question inside this room here as a technical community, but what I believe is when I walk out the door, walk down the street, and I actually interact with the general public, what I think is the game changer there is sustainability. That we really are going to have this driver that says everything that we do and how we view the technology is about sustainability. And to me, that means actually three factors. It's social sustainability. What are the technologies that make this affordable to everybody? And it's not a luxury Western privilege that we have for this. How to make it financially or economically sustainable, that the whole ecosystem actually profits, that the profits and there's money flows into the research institutes to the end users. And then, of course, the third part of sustainability, the environmental sustainability, which is the hot topic. So I believe that when we walk out the room and we engage with the real world outside of this bubble, that it's sustainability that's going to drive and change everything we do over the next, let me say, 50 years.
I have another point. So we have learned that AI/ML is one of the key topics. Now AI/ML is driving algorithms, is supporting the optimization of algorithms, but what may happen in the next future is to have the implementation of network devices or part of the network devices, the implementation that has been done using some AI/ML tools. So for instance, instead of part of a receiver like the equalizer or the channel estimation, now it's designed by very skilled engineers. The layer 1 implementation is one of the most complex part of the radio access network. Now think about the equalizer that has been designed by an IML algorithm, and so you have to trust it, you have to test it, but of course this can be a real game changer in the next future.
Yep.
My point of view is a little bit a second level point of view, because what we see, it's basically that the investment in creating data center is growing double digit. So for us, the data center was a market that was basically zero value. Now we are talking about a market that is growing, and now in this moment for 2024 we are talking about hundreds of billions. So only an investment in data center made by Facebook, Netflix, Google, so the big operator. Obviously, we sell to them cables, every kind of cables. But if they buy today cables, is because tomorrow they will sell services. So the fact that they are investing so much and so fast, basically aggregating more than 50% of the capacity of the cable maker in the world, it's a clear signal. Sooner or later, we will convert this in services.
Yeah.
It's a matter of time.
Yeah, just to make you an example of what I mean regarding the sustainability. I've been listening to a presentation by Cadence. Probably you know Cadence as a, let's say, CAD vendor. Let me say one that probably the biggest one. And they are introducing very heavily artificial intelligence. And they one of their most important customer is NVIDIA, as you may know. NVIDIA is one of the makers of the processors for artificial intelligence. So therefore, what is happening is happening that the life cycle of design for this kind of chips is being shortened and shortened. And this will drive an increase in performance of the let's say, machines that actually aid the computer design of themselves. And this is a cycle. At some end, this cycle will have to break. Cannot be sustained. Okay, so I do agree on the sustainability point that you raised. That is energy sustainability, but also of other kind of. Okay. Yeah, I think we are quite close to a conclusion. So, yes. Antonio, if you want to draw your.
There's a question.
Oh, there's a question? Yes, please. Yeah.
Thank you very much. This is just a curiosity on my side. So, like you said earlier, you are all companies, so your purpose is to make money. All this machine learning, artificial intelligence, is it something that your customer asks from you, let's say directly? So they come to you and they say, I want a spectrum analyzer equipped with AI, or it's more that the customer wants something. I want a 300 gigahertz spectrum analyzer, and AI is the way to make that happen.
I think there's two sides to that. So there is the test tool for AI. So part of it is AI needs a test tool, and then there's AI for test tool, the inverse round. So yeah, for AI for test tool, it's more driven by, let me say, the test and measurement industry, that we need to follow this trend and utilize the technology. But certainly on the other side, test tool for AI is driven by the customer, saying that as I implement AI, how am I going to test it? So we face both.
I can say the same. We see both the cases, but I can see that we see mainly the case where the customer comes with a need, and in some cases this need can be satisfied immediately only with some automation and with some artificial intelligence. So it's the case of the frequency reuse. Indeed, for example, so it's driven by network architectures that vary over the time, that evolves, but it's also driven by economical reason. So one customer of ours has this economical reason and economical requirements, and as the equipment were not yet ready to address this strong requirement, we adopted a solution based on AI. So it's both, but exists also the case where there is a need and you can satisfy it with artificial intelligence only.
Yes, as a tool vendor in general, AI is a way to speed up the development cycle of our customers, which means make it easy to find issues, solve them, retest, and so AI is pretty pervasive and is a common request from the market, and also is part of our implementation in our testing solution. So it's straightforward.
I agree with my colleague.
I can answer to you saying, of course, customers want AI in the products that we deliver, but I would say for two reasons. Some customers, the technical ones, they know the value that it can bring. Some others, you know, it's like the story of putting the AI label on something and you sell it. Okay, so.
Yeah. Okay, thank you all for the participation and your valuable contribution to this portion of the day, and thank you again.
Thanks.
Give the microphone to Antonio that is going to.
Thank you. So we have the last effort, but very interesting one, because we now have the very quick 5-minute speeches of the shortlisted contributions to the Best Contribution Awards mid-project of Restart. Today we have the pitches corresponding to the best scientific contributions, and tomorrow morning at 8:30. So be here in time, and otherwise you will feel very guilty of being part of Restart and not participating to the presentations. So we will have the pitches for the best impact contributions. So we start exactly in the order I already provided to all the speakers. So 5 minutes, and yes.
Okay. First of all, today I will present this paper, which is called Morpheus, a runtime compiler and optimizer for software data planes. I want to start by giving you, it doesn't work. Okay, by giving you, there were some animations which are not working, okay. By giving you some information, some context on what we are talking about. In modern networks, a lot of functionalities today are implemented in software. We have software switches, software firewall, intrusion detection system, load balancer, container networking interfaces, DDoS mitigators, which are implemented as a software programs running on general purpose servers. Now, if we look at the traditional way to implement these functionalities, we can say that what we do is to write our applications into an high-level language, and then this application contains the entire data plane semantic, which means how to parse a given packet, how to read the headers, how to get information from tables, configuration information from tables at runtime. Then, after we write our application in this high-level language, what we do is to take a compiler that can be a standard compiler like GCC or LLVM, no, which are compiled used for general purpose applications. And this compiler will emit a new data path, no, which is a binary that contains the information on the application itself. And then we get the information or the runtime, the configuration of our application from tables, depending on this data path. And this data path is general enough to get every type of configuration or runtime data. I don't know why. No, there were some animations, but they are not working. Can we? Is it with the PowerPoint or? If we take this information back into the compiler and we make the compiler aware of what are the runtime information that our application is receiving, for instance, the runtime configuration of the application or the runtime traffic that the data plane is actually receiving, we can create a compiler, which is the purpose of this paper, which is called Morpheus. I don't know if you can read it. No, it's in the middle of the box. And this compiler is a dynamic compiler, so we are introducing a new way to generate network applications, which are able to automatically generate and automatically create a new data plane, which is customized according to the runtime behavior of the application. So, depending on the runtime traffic or the runtime configuration, we generate every time a new version of the application which is customized and tailored for the runtime settings. So just let me give you a brief example. Let's take the case of an intrusion detection system. And let's say that we configure the data plane in a way, or we write the application in a way that handles all the type of traffic. But now let's suppose that this configuration of the ACL table into the data plane is configured only with TCP rules. Now, of course, when we write the application, we don't know which type of rules the table contains. So the application should be general enough also to handle UDP traffic or other type of protocols. But if our compiler is able to understand what is inside the table, so the runtime configuration, we can modify the source code of the application by skipping the table lookup for UDP traffic and just go straight at the end of the pipeline and apply the default action, which means we can save a lot of resources, we can save CPU cycles and improve the performance. At the same way, depending on the traffic, not only the configuration, if we have a traffic where 5% of flows receive 95% of traffic, we can create a sort of cache and we can accelerate the application by returning directly the result with the flows that are matching directly on the cache. So this is what we built in this paper. We built this compiler that is working at the LLVM intermediate representation. This compiler performs 3 different steps. The analysis step, which understands the application. Of course, the application can be every data plane application, so the compiler understands what the application is doing. Then there is an instrumentation phase where we put additional information to gather runtime information from the data plane. And then there is an optimization step where we recompile the application and we create every time a new optimized data plane. And of course, we repeat this process every time. Just looking at the result, we managed to improve performance of the application from 5% to 95%. And these applications are also applications used by hyperscalers. For instance, Catran is a load balancer used by Meta in production. So we showed that this compiler is able to optimize real data planes depending on the runtime traffic and runtime configurations. So thank you. Of course, Morpheus, so we need to thank you, Morpheus. Thank you very much.
Jacopo is next. No, don't do it.
Okay.
Okay, so good evening, everyone. This work is on joint communication and sensing and about a way to make it practical to use joint communication and sensing with unsynchronized transceivers. So let's look at joint communication and sensing in a bistatic scenario, which means you have a transmitter and a receiver which are entirely separated, okay? And we talked a lot about joint communication and sensing today, so you know the aim is to sense some parameters of a target by using a scattered wireless signal. So we transmit a signal, we receive a reflection, and we want to estimate some parameters like delay, Doppler, and angle. The problem is that one may think that you can just apply radar algorithms out of the box and get those parameters. But the issue is that in communication networks, transmitter and receiver are not synchronized. And this is causing a lot of problems on applying radar algorithms because you will have timing and frequency offset that are derived from the asynchrony in the clocks in the two devices, okay? So the estimation of those parameters is not possible directly. And we need a practical way that can be implemented in any device in order to solve this problem. So what is actually asynchrony doing on the joint communication and sensing? So first of all, you will get a wrong estimate of the delay, which gives you an apparent target which is not in the right position. So you do not measure the correct distance to the target. And you have a corrupted Doppler spectrum, okay, which looks something similar like in the picture, which is not really representing the Doppler of the target, but is rather covered by the carrier frequency offset, okay, which is affecting the phase of the signal. So we need to solve this somehow because this is one of the biggest, if not the biggest, issues in really implementing joint communication and sensing in networks, okay, in mobile networks. So our approach starts from the idea that actually if you look at these offsets, they are due to the receiver device, not really to the channel. So they are the same on all the multipath components that you have in the signal, okay? So the idea is if we can just take one of those multipath components that we identify as an anchor point for our processing, for example, it may be the line of sight or any other static reflector that is sufficiently strong, we can detect it, estimate the offsets, okay, and then cancel them out with a very simple processing at the receiver. So the good parts about our algorithms that are, let's say, improving over the literature is that it's accurate because from a very strong reflector we get accurate estimates of the offsets. It doesn't have hardware requirements in the sense that it doesn't require multiple antennas at the receiver, for example, which is a requirement of other approaches. And it preserves the linearity of the subsequent estimation. So you can implement it with very low computational complexity. And this is an example result that we get. So we implemented this over an FPGA-based software-defined radio. And in the top plots, you can see what we get in tracking a person that is walking around the room with two completely independent devices, as you would have in a mobile network. And in the bottom plot, you can see what happens to the Doppler spectrum when you use our method in order to clean up the phase from the frequency offset. And from what before looks like, let's say, a random Doppler spectrum, we get something which is kind of typical of human walking, okay? So this is something that people working on sensing can recognize quite easily. This concludes the presentation, and this is a QR code if you're interested in having a look at the paper.
Thank you. You have a go. Next is, let's see, Federico Masson. Federico, please. 5 minutes.
Okay. Okay.
Go ahead.
Okay, thank you everybody for being here at this time. So today I will present a work that me and other colleagues from the University of Padua are being carrying out in this first half of the project. And this focus, the focus of this work is using artificial intelligence at the edge of the network, which is something that everybody is considering nowadays, and in many presentations of today we heard about. And the idea is that if we're using a learning agent for orchestrate resources at the edge of the network, like bandwidth, to be allocated among a group of users, we need to periodically retrain the agent, especially if the environment is changing in time. Like if we consider a network slicing scenario, or a scenario where we have different users associated to different service class, we need to refine the agent policy in case a new slice, for instance, so a new class of service is added to the systems. And in order to do so, the approach that is normally considered in the literature is to perform some continual learning strategies, so is to allow the agent to be refined in time, collecting new information from the system and update its policy, so making it able to manage a new scenario that it did not see in the past, using also the knowledge that the agent already have. However, to do so, we need computational resources. We need computational power in order to train the agent, which means that we need to send the training data from the edge of the network to the core network, where we have the data center or the other computational facilities that we can use for such a purpose. But the problem here, which is something that affects all the communication system that consider a learning agent at the edge, is that we are using communication resources. We are using part of our network resources for training the agent, which is something that normally in the literature, in the industrial community, is not considered, but it means that we are taking away some resources from our users, whose performance is our final goal, in order to make our system more adaptable, more flexible in time. And this is a kind of a contradiction that has to be considered when we implement artificial intelligence in our networks. And to solve this to kind of address this problem, in other work, we consider two possibilities. The first, which is trivial, is a static solution, which means that every time the environment changes, we just allocate a predetermined determined amount of resources for the training of the agent. And the second one is an adaptive solution, which means that when the environment changes, we try to estimate the accuracy of the agent action. In the case of our reinforcement learning paradigm, we can consider the temporal difference error in the estimation of the q-values for the people that are used to use reinforcement learning. And then we decrease the amount of training data, so the amount of resource that we take away from the users in order to train the agents, as the training improves and as the performance of the agent improves in times. Looking at this, if some of you is used with reinforcement learning, will immediately think about the trade-off between exploration and exploitation, which means that any time that we are managing the system, we can decide if we improve the exploration of the system, so making the agent to perform random action, or improve the exploitation of the agent policy, which means that we increase the performance of the end user, we increase our probability to get a higher reward. This is not the same trade-off, it's something new. It's like adding a third path in this trade-off, which means that at any moment that we are managing our system, we can choose if we want to improve the exploitation, the exploration, or the effectiveness of the agent training, which introduce a new challenge in the design of future communication systems. This ends the presentation, and we already published 3 papers on this, and if some of you are interested, just send me an email. Thank you.
Very well. Next is Marco.
So, thank you. So, it's again me. So, it will be quite fast, since you already saw many of these things in my previous talks. So, this is integrated communication and imaging, design, analysis, application, 6G networks. I would like to thank my colleague Francesco, Maurizio Magarini, and Stefano Tebaldini. So we would like to propose a new paradigm. This new paradigm is integrated communication and imaging. Usually it's like integrated communication and sensing. And by imaging, I mean the formation of detailed, accurate, high-resolution radio images of the environment by exploiting some kind of waveforms that are either custom waveform or like OFDM waveforms that are able to carry information. And what is the difference between sensing, let's say classical sensing, and imaging? This is a sort of my opinion, let's say, so it's not like a dogma, but to me, classical sensing involves the estimation of a few targets, like range, angle, and velocity in the scene. Like the main results usually in like sensing paper, the final results in the final section is like a table with, I don't know, 20 entries for all the 20 targets with range, angle, and velocity and their respective variance, for example. In in our case, the final results in that, let's say, hypothetical paper, the results is an image, and the performance is related on how well the image is focused, how well the targets are focused, and possibly the target are an infinite amount of infinitesimal scatter, each one with its own radar cross-section, its own position, and its own velocities. This imaging can be done for whatever platform, from the ground, from a vehicle or a base station, a fixed base station, and from the stratosphere, and passing also in the middle with mid-altitude platform, like, for example, UAVs. And as I said before, this is the same image as before, just a little bit bigger. This is what I mean by our final results. These are SAR, synthetic aperture radar image of the environment, with an infinite amount of targets, of infinitesimal targets. Each target, even the smallest one, just interacts with the electromagnetic wave, and the echo comes back to the receiver, and you can then focus your image, and you get something like that. And you can use it then later on, however you want, you can ingest these kind of images in a machine learning algorithm. You can detect targets over there. You can detect targets under rubble after an earthquake, under snow after an avalanche, if there is someone is lost in the forest, you can detect it under the forest. So you can exploit this image with whatever algorithm you want, and you generate this kind of image, and just you inject it in this algorithm to exploit and to use for whatever application. And it's very different from optical. Optical is still something very useful, but that image, that radio image, just gives us a new perspective on the scene, something new to look at and to exploit. And the paradigm that we use, we cycle through this paradigm. We start from an application, we think about an application, search and rescue in remote and non-connected areas, for example. We want to do network offloading, environmental awareness, and so on. We develop some software, some simulation, the realistic simulation. We do problem modeling, algorithm development. We design simulators. We do waveform design, and so on. We assess the performances, and then we really want to see if these things works or not. And we go with hardware development. So we take a manned aerial vehicle. We develop radars, Radcom devices. We collect a lot of real data. And so we can see if what we think it works and what works on theory really works in practice. And this is, let's say, our work. And all the time we solve a little problem, or there is something new to publish. We try to publish this. And as you can see, we have quite a good dissemination record. We bring all the little details that allows us to let integrated communication and imaging work. We bring them to conferences around the world, from the US to Italy, Germany, Greece, and we publish also several journal papers for all these aspects. So that's it. I was quite on time, so thank you.